Hello, everyone. I'm going to get started so we can stay on track. We have a full session, full slate of talks today at RocqPL. So thank you to coming to this inaugural session edition of RocqPL. It's my pleasure to start things off with a bang. Our keynote speaker today is Arielle. So Arielle Kellison is a senior research engineer at CodeMetal, where she works on ensuring the correctness of LLM-generated code using methods from programming languages, formal methods, and numerical analysis. She received her PhD in computer science from Cornell University in December 2024, and subsequently held a postdoctoral appointment at Sandia National Labs. From 2020 to 2024, Arielle was a Department of Energy Computational Science Graduate Fellow, and in 2025, she was named a Frederick H. Howes Scholar in Computational Science and an MIT EECS Rising Star. And today, she's going to be talking about some of this work on future-proofing numerical accuracy with formal specifications. Thank you, Arielle.
I think my mic is on, yes. I'm really delighted to be here today, and this talk is about some of the work that I did during my PhD on writing formal specifications in Roc with accuracy guarantees, specifically for numerical linear algebra programs, and how I think the Roc community can help with future-proofing numerical accuracy guarantees by writing formal specs in Roc, specifically in the domain of numerical linear algebra. So to start off with, informal specs have played a very important role in numerical linear algebra, and particularly in its success over the last 75 years. And numerical linear algebra has been incredibly successful, so it works astonishingly well. And kind of the canonical, or one canonical example of that, is solving large systems of linear equations. So in this setting, we have like a coefficient matrix A. And we're also given this constant vector b, and we're tasked with finding a solution vector of variables x. And this is like a very important problem in science and engineering. So for instance, it's used in public health models for modeling disease transfer. It's also used in weather forecasting and supercomputing benchmarks. So for supercomputing benchmarks, people solve these giant linear systems of equations to try and rank supercomputers and by how performant they are. So how well do they solve, how quickly do they solve these really big systems of equations. And kind of the remarkable or astonishing thing, I think, is that I can solve pretty much like a dense linear system of equations where the dimension of the matrix is like 10,000 on my machine that I'm presenting on today in around a minute, which is really kind of incredible, especially considering that 75 years ago, a 12 by 12 linear system of equations was given to the mathematical division at the National Physics Lab in the UK, and it was considered an incredibly challenging problem. And you might think like, okay, incredibly challenging for whom? You learned Gaussian elimination in middle school, like why is this hard? Well, it was incredibly challenging for some very influential people. So James Wilkinson was tasked with working on this problem, and he won the Turing Award in 1970, partially for his work on it. And he was working with Turing on this problem at the mathematical division in the National Physics Lab in the UK. And in his Turing Award speech, he says, Turing was not particularly enthusiastic about solving this 12 by 12 system of linear equations, which you might think is simple these days, particularly because he was convinced that it would be a failure. So this leads us to a very natural question of, well, why does numerical linear algebra work so well between especially like solving these 12 by 12 systems of equations being challenging 75 years ago to being incredibly practical on our machines today? Okay, well, clearly the intuitive answer off the top of your head is going to be that advances in hardware have delivered like incredible performance over the last 75 years, right? So as a kind of proxy for hardware performance in general, here I have a plot of the top 500 supercomputers, the top 500 machines in the world, and how their like arithmetic intensity. So here, actually, this is a plot of flops per second, so floating point operations per second. This is 35 years ago in 1990 is where it starts, and 2030 is where it ends. And you can see that we go from 1 gigaflop, so 10 to the 9 floating point operations per second all the way to an exaflop, which we were able to hit in 2025 on our top machine. So an exaflop is 1 billion floating point operations per second, or a quintillion floating point operations per second. So like clearly advances in hardware have had an impact on the success of numerical linear algebra. That's a really intuitive answer that's sort of obvious in some ways to most people. There's another answer, okay? Advances in algorithms have kept pace with the hardware. So for example, we moved from vector processing machines to hierarchical memory, and numerical linear algebra had to sort of refactor many of the common algorithms. Like here I have a simple matrix multiply, you know, a triple nested loop, and we had to refactor this to work on these hierarchical memory machines. And in particular, we wanted to increase arithmetic intensity by, in this example, blocking matrices to reduce the amount of data that we moved. Okay, second intuitive answer, right? Advances in algorithms, clearly, computer science. But there's a third answer that isn't maybe intuitive to most people, but is really well known in the numerical analysis community, which is the basic linear algebra subprograms, or BLAS. I'm going to continue to say that. Standard provides a stable interface. So in particular, we have these clients. So at the beginning of the talk, I said linear algebra is used across science, in engineering and science. So we have these clients, which are applications, scientists, and library developers, common like NumPy, PyTorch, for example. So at the top of this stack, on top of the BLAS interface, we have these clients in science and engineering, and then the BLAS interface provides for them an abstraction where we have over these very basic linear algebra kernels, like a dot product, a matrix multiply, matrix vector multiply. And really what this does is it provides an abstraction that clients can rely on. And then below, providers, mostly hardware vendors, so providers of these basic linear algebra subprograms libraries, they can aggressively optimize while clients can rely on the stable BLAS abstraction. And yeah, mostly the providers are hardware vendors. So like Intel has its one API that has like a BLAS implementation in it that's highly optimized for their hardware. NVIDIA has CU BLAS or cuBLAS, which is highly optimized for their hardware. But then there are some academic offerings of these libraries as well, so OpenBLAS and Bliss. But for the most part, the providers of BLAS implementations are the hardware vendors themselves. All right, and you might think, well, why would I actually need to use something like BLAS? Why would I actually want to rely on someone else to optimize what might seem to use something simple like a dot product or a matrix multiply? And the answer is that well, we have these naive implementations. Again, here this is flops on the vertical axis and optimization technique on the horizontal axis. And if you can see that in the naive case, right, we don't really have great performance. You can add in these optimization techniques that might be simple to think of, like SIMD blocking, like we saw the matrix multiply earlier, threads. But then here's OpenBLAS. That's one of these publicly available providers of basic linear algebra subprogram interface. And we get very, very good optimization in comparison to these simple techniques that you or I might implement naturally. All right. So what does the BLAS standard define? Well, it was introduced in 2001, and it's really a synthesis or a composition of many previous attempts to provide specifications of the basic linear algebra operations. So in the late 1970s, they came out with this level 1 BLAS spec, which describes specifications of scalar and vector operations. For example, I have this scaled dot product on the screen. And then in the late 80s, they came out with a level 2 BLAS, which is matrix vector operations spec. And in 1990, again, kind of addressing the rise of hierarchical memory, they came out with a level 3 BLAS, which is matrix multiply operations or matrix operations. And then the BLAS technical forum standard is the composition of all of these things. It provides a high-level spec for all of these types of operations. So level 1, level 2, and level 3 BLAS. And it really was a meeting of a lot of people working on numerical linear algebra and also in the application space to try and decide what is the best high-level specification for application users for these types of operations. All right, so more specifically, the BLAS standard provides a fixed interface, so naming conventions and arguments, and I'm realizing this is a little bit small on the screen here, but this is an example just like of a summary of the BLAS 3, so matrix-matrix operations. And so the BLAS standard provides a fixed interface, a naming convention, so this is GEM, general matrix-matrix multiply. This is the example that I have at the top of the screen here. So really what it does is it scales the matrix multiply, and then you add on a scaled matrix to that. And it also provides a family of precision and type variants. So you might want to be able to do this matrix multiply in single precision, double precision. You might want to have matrices with complex numbers, for example, and so it has also options for single complex and double complex. And then it also specifies the mathematical intent, which I think is an extremely important thing here, but it really has for each operation, it'll have just a basic equation, and I have the basic equation for GEM that is specified by the BLAS here. All right, but there's a little bit of a gap here, so computed results don't always align with mathematical intent, right? So this is like our mathematical representation of that scaled matrix multiply, right? This is mathematically what we would compute in infinite precision given that equation. But here I have this C hat. Okay, so every element of that matrix C, when we're actually computing this on a computer, is represented in finite precision using a floating point representation. So this is a floating point representation. We have a sign bit, exponent bits, and a fraction bit. So that's every component of our matrix is going to be represented in this way. And there are many different formats that we might use each element would take. So we're probably most familiar with the IEEE double, which has 11 bits of exponent, 52 bits of fraction. Sometimes we use IEEE single, 8 bits of exponent, 23 bits of fraction. And then now, mostly this is used as a storage format, but it's becoming increasingly used actually for the computations themselves, is half precision, so FP16, where we have only 5 bits of exponent and 10 bits of fraction. Okay, so we have these decreasing precisions. All right. And really, what numerical analysts are concerned with in some instances is computing the error, so the difference between our ideal or infinite precision result and the computed result that's represented in floating point. All right, what does the BLAS standard say about what the error should be? So what is an acceptable difference between the ideal or mathematical intent that they specify and the actual result of the implementation? So the standard says that any implementation that produces results that are close enough to the usual algorithms presented in a standard book on matrix computations is acceptable. Okay, so let's suppose we have an implementation and we want to know whether or not it satisfies this informal specification regarding error or accuracy that's given in the BLAS standard. Okay, so let's go to a textbook. They say we can go to a textbook, and we should be able to decide whether or not the error that's produced by our implementation is acceptable. And we can maybe think of it as being acceptable if it's in the same limit as is specified in a textbook here. So this is a theorem from a standard numerical analysis textbook. It's the error for matrix-matrix multiplication. And here we see they have their inverted hat. That's our floating point matrix. And they're saying, okay, well, the error, so the difference between our computed result and the exact result, that's this AB, is going to be something like delta C, which is a matrix, where delta C is bounded by the true matrix multiplication, so the ideal result, and some constant gamma k. All right, so, well, we need to know what is gamma k. We'll go back in the book and we'll find the definition. Gamma k is defined as, for all n here is the inner dimension of the matrix, the matrices. For all n, and so long as n times machine epsilon, where machine epsilon is the relative rounding error for a single floating point operation, and it's dependent on the precision of your format, so it will change for double versus single precision. So long as the dimension of our matrix times machine epsilon is strictly less than 1, then we can define gamma sub n as this formula. All right, well, we have to look at this assumption carefully. So it turns out that textbook error bounds don't apply for low precision. So in this plot here, I have matrix size on the horizontal axis, and this matrix size times the machine epsilon for varying formats. So we saw floating point like a 16-bit, 32-bit, and 64-bit formats, as well as this B-float. So that's like Google's tensor processing unit version of the IEEE 16-bit format. So these are all plotted, right? And we see that like for pretty small matrix sizes, so this is 100, so where the matrix size is 100 and this is 1,000, like for pretty small matrix sizes, we have n times machine epsilon is 1. So that means, in particular, that accuracy in low precision regimes is pretty much unspecified by the BLAS standard. All right? So that brings into question, right, this statement that providers of the BLAS interface can aggressively optimize while clients rely on a stable interface. So in particular, our providers might want to aggressively optimize by using lower precision formats. Okay? And well, some clients really do need, they have error requirements, right? So I might have a client who requires error strictly less than some bound. And this isn't just like an academic exercise, so there are plenty of examples in the literature. So for instance, in weather forecasting, low precision linear algebra produces completely incorrect results due to insufficient accuracy. So if we want to use something like lower precision IEEE FP16, it won't be sufficient in this domain. All right, so here we have an example of where a client requires an error bound for their results to be correct. And the BLAS interface doesn't really provide that, right? So ideally, providers would ensure the accuracy or provide some guarantee, published guarantees about the accuracy of their BLAS implementations, but you won't be surprised that they don't. Okay. So this is where I think formal specifications can help align BLAS implementations with their mathematical intent. And I have some evidence to support the claim that they actually can. All right, so in particular, we developed LA-Proof, which is a library of formal proofs of accuracy and correctness for linear algebra programs that connects functional specifications of linear algebra implementations to accuracy guarantees, and we use RocqPL. Okay, so what does LA-Proof define? Well, LA-Proof defines floating point functional models and accuracy theorems for BLAS operations. So we have vector operations, the BLAS 1 level operations. We have matrix vector operations, and we also have matrix operations. So this is following that BLAS level 1, BLAS level 2, BLAS level 3 set of ops. And functional models, okay, so what is a functional model of a BLAS implementation? Well, it is a functional program in Rock. So here I have a definition of a dot product, and we use the mathematical components library to write our functional specs. So here, x and y are our vectors, a row vector and a column vector, and we're computing the dot product between those. And maybe it is a little small on the screen, but on line 5, we take a floating point sum. On line 6, all our multiplications in the dot product are binary multiplications over floating point values. So this is a floating point functional model. It takes floating point vectors, and it computes a floating point result. Okay, so we can connect our functional specs to accuracy guarantees by relating a floating point functional model to a real valued functional model. So in particular, these are like the same format, right? In many ways. Here on the left-hand side, we have a floating point dot product, so our floating point functional model. And then on the right side, we're everywhere where we had f type t, everywhere we have a floating point type, our real valued model of that is just instead defined over the reals. All right, And so there are really two kinds of accuracy theorems that we prove. Forward error, which is really very intuitive in the sense that you want to compute the distance between the results. Right, so I have my real dot product over an input, my floating point dot product over an input, and then the forward error just tells you the difference between the floating point and real valued or infinitely precise result. But in numerical analysis, we're also concerned with what's called backward error, which essentially measures the error in the input space rather than the output space. And this is very useful in a lot of physical science domains where the data that you're computing on itself has some kind of error due to measurement, for example, and you want to be able to compare the error due to measurement to the floating point error that's accumulated over a computation. All right, so once we have our real functional models and our accuracy proof, we can connect our functional specification, which is our floating point functional model, directly to implementations by proving a refinement proof of a C implementation of our floating point functional models using something like VST and RocqPL. And so we do this in LA proof. We provide an example of connecting our accuracy guarantee directly to a C program that's a sparse matrix vector multiplication. All right, so what are the criteria for useful accuracy theorems? Suppose you wanted to prove an accuracy theorem for a linear algebra operation. Well, there are four that we've kind of determined are specifically interesting or needed criteria for useful accuracy theorems. The first one is soundness. That's not surprising. Secondary to that is that the accuracy theorem should provide a tight error bound. Third is they should be broadly applicable. And finally, compositional. All right, so useful accuracy theorems are sound. What does this mean? In an intuitive way, I have a plot here where errors are these, so like empirically observed errors for a matrix-matrix multiplication. Errors that are observed are solid lines, and error bounds, that's like a theoretical bound that we've proven, is going to be the dashed line. What does soundness mean? Okay, it means that your error bound should always be an upper bound to the observed error. Okay, so how do we actually guarantee sound bounds? Well, first we use a faithful formalization of the IEEE 754 semantics for floating point arithmetic in RocqPL. So this is provided by the flock library, a floats for coq library. And what are the semantics of floating point arithmetic, or specifically floating point operations that are provided by the IEEE standard? Well, it says that every operation shall be performed as if it first produced an intermediate result correct to infinite precision. So that's the usual infinitely precise computation that we would think about for a single operation, and with unbounded range, and then rounded that result according to one of the attributes in this clause. And so the IEEE standard defines essentially 4 rounding modes where there are some variance on this round towards nearest. And here I have an example of round towards nearest. So if this is my real number, I'm going to round to the closest float. But it also has some other rounding modes, 3 others in particular: round towards 0, round towards positive, and round towards negative. So these are the rounding modes that are described for floating point operations by the standard, and they are integrated into the flock library. Okay, so what does this mean for a specific operation? So what it means is that in RocqPL, we can prove accuracy theorems for each basic floating point operation. So here I have a accuracy of a floating point multiplication. What it's doing is it's taking 2 floating point numbers, and it's saying as long as the result of the multiplication is finite, so that means it doesn't overflow, it can fit inside of the format that we're rounding to, there exist 2 error terms, and we can exactly represent a floating point multiplication as the real multiplication scaled by some error plus some additional error value, and we have bounds on those error values. And here, in LA proof in particular, we define the binary or floating point multiplication as using round towards nearest. All right, so how do we actually guarantee sound bounds in practice? So of course, yes, we use this faithful formalization of the IEEE semantics. We also connect bounds to real C programs using VST. But if you actually wanted to guarantee that your bounds are always upper bounds for every possible execution of a program, you need to use a proved correct compiler that also respects the IEEE semantics. And then you also need to execute on IEEE 754 compliant hardware. All right, so that was soundness. The second criteria is that useful accuracy theorems are tight, so that it means they're not overly pessimistic. So if we look at this plot again, where our solid lines are observed error and our dashed lines are error bounds, then tightness means that smaller is better. We really should ideally have some very small delta of difference between our observed bounds and our sound error bounds. Because, for instance, I could just say an error bound is infinity, and this is not useful at all. Third, useful accuracy theorems are broadly applicable. They're not overly restrictive. So an example of an overly restrictive accuracy theorem that we saw previously was one in which we had this assumption that the size of the matrix times the machine epsilon, so the format that we're computing in, is strictly less than 1. And this was overly restrictive in the sense that regarding the assumption of it being strictly less than 1. And finally, useful accuracy theorems are compositional. So for example, we had our dot product functional model, and if we define a matrix multiply in ROCq, it's going to use probably that dot product. And so here on line 6, we're using the dot product inside our matrix multiply, and so we should very easily be able to use any accuracy theorem about the dot product, so relating this floating point functional model to its real functional model. We should be able to use that accuracy theorem in a very simple compositional way inside of the accuracy theorem for a matrix multiplication. So now this begs the question, does LA proof provide useful accuracy theorems in practice? So we have a case study where we used LA proof to prove the accuracy and convergence of a linear solver, so a solver for a linear system of equations, where it's actually called the Jacobi method. And the problem is, something we saw at the beginning of the talk, we're given a coefficient matrix, we're given a constant vector, and we need to find the solution vector. And what the Jacobi method does is it takes the diagonal elements of the matrix A that we're given, and it iteratively updates the solution vector using matrix vector multiplications. So at every step, we use a matrix vector multiplication. And so this is a case study where I will argue that LA proof does provide useful and accuracy theorems in practice. So this is a plot provided from a PhD thesis that my colleague wrote, actually, on proving the accuracy and correctness of the Jacobi method. Okay, and so blue line down here is the computed error over iterations, so where iteration is k. And then up top we have our theoretical error bound, so the error bound that he was actually able to prove, using LA proof for each of these matrix vector multiplies. Okay, and that clearly this is sound, right? Our theoretical error bound is a sound upper bound to the observed error. It's fairly tight. It's actually nicely surprising. It's only a factor of 2 larger. And it's compositional in the sense that we were actually able to use LA proof, right? This is multiple iterations where we have to use our matrix vector multiplication accuracy theorem. So it's compositional in the sense that we were able to use all of the accuracy theorems for the basic linear algebra operations that are provided by LA proof to prove a tight and sound accuracy bound for this iterative method. All right, so that's 3 of the 4 criteria. But are they broadly applicable? This is only one case study. And I argue in some sense they are, specifically because, now I don't actually expect you to read this at all, but this is our theorem on the matrix multiplication error, so the accuracy of the matrix multiplication in ROCq. And if you wanted to, you could go and look through it. But what you will find is that we don't actually have this assumption from a textbook error bound. We didn't need to make use of it. And actually, at a high level, it was very nice because what happens is that numerical analysts, it's kind of a pain to take care of all of the higher order error terms that appear in a very large error analysis of something like a matrix multiply. And what they do is they use classical identities to try and account or capture higher order error terms in a really easy way to do on paper. But when we use a proof assistant, we can kind of do all of that accounting without having to worry about things being incorrect. So we didn't have to actually make this assumption at all in our proof. So in some sense, LA proof error bounds are not overly restrictive in the same way that they would be from a textbook proof. But they might be over-restrictive in a different way. So applications, that means application scientists, people, clients of the basic linear algebra subprograms, they're embracing stochastic rounding. So for example, in climate modeling is a place where people really want to use stochastic rounding. This is a different type of rounding from the 4 formats that the IEEE standard specifies. And what these people say in this study is that they looked at the efficacy of low precision arithmetic for climate simulations. And by testing models using both round to nearest, so that's an IEEE standard rounding mode, and stochastic rounding, we found that stochastic rounding can mitigate rounding errors across a range of applications. And thus, our results also provide some evidence that stochastic rounding could be relevant to next generation climate models. Many application scientists outside of climate modeling as well are really finding that stochastic rounding has a lot of benefits, especially when you're using a low precision in your computations, and they want to use low precision because it makes things faster. Hardware is also embracing stochastic rounding. So there are a few examples, like the GraphCore IPU supports both IEEE half precision and stochastic rounding in hardware. AWS's Trainium also supports IEEE half precision, not just for storage, but also for computations, and uses stochastic rounding or implements stochastic rounding in hardware. But LA proof does not support stochastic rounding. So in some sense, are our accuracy theorems really applicable to like next generation computing? Are they really providing the kinds of accuracy theorems that application scientists will want? And the answer is no. And again, before we had this lemma about the accuracy of a floating point multiplication, and I said like we define it assuming round to nearest. Okay. So this is where we find the need to future-proof accuracy guarantees. So I think that stochastic rounding provides an opportunity to us as people who are interested in writing formal specifications for software, but also for hardware. So in particular, it provides the opportunity for us to isolate rounding mode assumptions. So some properties that are trivial and round to nearest, so a lot of properties that are like trivial and numerical accuracy theorems that use round to nearest don't hold under stochastic rounding. And other properties of round to nearest do continue to hold under stochastic rounding. And I think that if we can isolate these properties systematically, then that will help us identify like which proofs in numerical analysis, and specifically which proofs in the accuracy of basic linear algebra operations are robust to new hardware rounding modes. And secondary, I think it presents an opportunity for us to extract reusable proof patterns. And I wish I could make this a little bit larger for you. But this is a theorem of matrix-matrix product accuracy where the authors are using stochastic rounding to prove a rounding error bound for matrix-matrix multiply. And the result that they have has the same overall structure, and the proof has a very similar structure to what you would find for a non-stochastic rounding, so for any of the IEEE standard rounding modes. And so the idea is that we'd really like to be able to extract like the proof patterns that a numerical analyst would use for any kind of proof about accuracy for linear algebra operations by looking at the similarities between linear algebra proofs of accuracy that use standard rounding modes and linear algebra proofs of accuracy that use these non-standard rounding modes. And I think that we can use stochastic rounding as an opportunity to do that. I think this is also important extracting reusable proof patterns because ideally we have robust, insightful, and easy to read proofs because these will help strengthen the argument for formal specifications in basic linear algebra in the numerical analysis community. And just anecdotally, I did a PhD with a numerical analyst where I was co-advised by someone who works in formal methods. And I would really write these like long proofs in RocqPL, right, of numerical accuracy, and I would bring them to my advisor, and he did not want to look at them, which is not surprising, right? He's a numerical analyst. He wants to know, like, what is the high-level, insightful thing about this proof? And so it is very important for us when we're trying to interface with people from other domains to try and kind of isolate the most insightful parts of our proofs. And I think that if we can extract the reusable proof patterns from our LA proof proofs, then this will very much help with making the argument for providing formal specifications in the basic linear algebra operations. Now, similar opportunities arise for non-IEEE arithmetic formats. So there are many kind of new next generation formats, arithmetic formats that people are trying to use in different areas of computing. Probably one of the oldest and most popular ones that people are discussing these days are Gustafson's posits. And there's been sort of a long history of argumentation about whether posits are actually a reasonable format to use for computing. And it's been sort of very heated in the numerical analysis community whether these are ever going to really be appropriate for computing at all. Partially because in order to use posits, numerical analysis will have to essentially be completely rebuilt. And while this is, probably a bad thing if you want to have reliable computing, I think that for us, it's a potentially useful case study for identifying pain points in formalizing non-IEEE formats. And again, so I said, like in stochastic rounding, one of the reasons I think that we should really be considering formalizing this and trying to like future-proof accuracy guarantees with respect to it is because both, it's application designers as well as hardware designers are requiring it or wanting to use it. They're embracing it. And just in the last year or so, a couple of years, in 2024 was the first multi-core RISC-V processor with a hardware implementation of posits. So whether or not people in the numerical analysis community sort of agree with the use of non-IEEE formats as a reasonable thing, I think it is probably something that will continue to be sort of emphasized by both the hardware and application communities. And that if we can, as formal methods folks, start to consider like what are the real pain points in formalizing these non-IEEE formats and what are the pain points of incorporating these formalizations into proofs, then we can kind of maybe provide useful ideas to the numerical analysis community. All right, so my argument really is that the RocqPL community can help future-proof numerical accuracy by formulating formal specs for linear algebra operations, so for the basic linear algebra operations. I made the argument that informal BLAS specifications have enabled decades of success in numerical linear algebra. They really have been consequential in the same way that new hardware improvements and new algorithmic improvements have been to the success of numerical linear algebra. And I think because of the role that informal specifications have played in that area, I think that we as people who are concerned with formalizing specs, that we have really an opportunity to try and interface with people who are designers and clients of BLAS. So accuracy is also left entirely unspecified by the BLAS standard, right? For low precisions as well as for new rounding modes and formats. I made this argument. And I think that as far as future proofing, what we can do is formalize accuracy theorems that include low precisions, as well as new rounding modes like stochastic rounding and potentially non-IEEE formats. And formal specifications, I make the argument, can restore accuracy guarantees to BLAS implementations. And we have an example of that in LA Proof, which demonstrates that BLAS level accuracy guarantees can indeed be mechanized and applied to real world programs. And my hope is that LA Proof can sort of serve as a template for extending formal specifications in numerical linear algebra, again, to include things like low precisions, which we can, our accuracy theorems do hold in LA Proof for things like low precisions, but extending them to include new rounding modes and formats I think will be very insightful for the numerical linear algebra community at large, but also very useful exercises for people who are interested in formalizing numerical accuracy in theorem provers like RocqPL. And so with that, I would like to conclude and welcome any questions.
We have time for questions. If anyone, feel free to raise your hand and we'll send a microphone your way. Okay, I can get us. Okay. You'll take the next one. Okay, so with these stochastic rounding things, right? I assume it's sort of randomized, right? So yes. Here, to get a tight bound, wouldn't you want to have some sort of, what do I say here, sort of amortized or average error analysis, or do you still want like a tight upper bound?
So the stochastic rounding actually provides a tighter upper bound in general, and that's why a lot of people or numerical analysts, part of the reason that numerical analysts have been interested in it historically, well, they've been interested in probabilistic error bounds historically, but those aren't necessarily sound. Mm-hmm. But if you use stochastic rounding and then you perform a probabilistic error analysis, then you can the sound bounds work. And really what's happening is when you're using something like round to nearest, the errors are often correlated. But when you use stochastic rounding, in the mean, right, your errors might actually cancel, and they do in practice often cancel out.
And that's not a probabilistic argument that they cancel out?
It is a probabilistic argument that they cancel out, yes.
And would that have to be reflected in the specifications?
That would have to be reflected in the specifications, that's right.
Got
yep.
It.
So there is, it's not grounding inside of the proof assistant. We will actually have to probably include different libraries for probabilistic reasoning and in order to support stochastic rounding.
Makes sense, thanks.
Yeah.
Can you? Sorry. So this is really cool. What can you say? So do a lot of people use C or C++, or what is the common things that people actually code this stuff in? And then I imagine a lot of them, Fortran. Okay.
Yeah, Fortran. No, but so earlier on, it was very small on the screen. But when I said, like, what does the BLAS standard define, and it has a standard interface, it's a Fortran API and a C API, and there are C implementations of BLAS. So people use C, they use Fortran. Now some of these are being ported to C++, but historically it's been Fortran and then C. So the idea that we can formally verify these programs is not completely absurd, right? If most of them are written in C.
Yeah, so coming back to the stochastic rounding, which I discovered in your talk, thanks. Is it really non-deterministic in that if you run the same program twice, you can get different roundings? Or is it kind of a hidden function? The rounding is an unspecified function of the values of the arguments, some kind of pseudo-random function, but still a function.
Theoretically, it is truly non-deterministic. So if I round a value, it will not always, the result will not always be the same. As far as the actual implementation, right, we may or may not have true non-determinism.
Okay.
Yeah.
Well, that makes a big difference for proofs like COMP-certs or semantic preservation proofs. So that's why I was asking.
Yeah.
Thank you.
Yeah. Yes, so actually connecting, any formalization of stochastic rounding in the proof assistant to real implementations is a very open question.
For certain problems like inversion of matrix, you can use an iterative process and you stop when some test is satisfied.
Yes.
So in that case, you don't have to propagate errors during the iteration process, because it's the stopping condition that will describe the precision. Is that the case, or?
Yeah. So if we go
in
back
my conversations with Mohit, it was the case, I believe. But,
yeah. So if you're computing the stopping condition also in finite precision, and the stopping condition is like for the method that Mohit was working on in this case. You're looking at the difference between the computed result and like some your ideal vector that you're given in the first place,
or between successive values in the vector.
You are looking between successive values, yes, yeah. And you have, but the user defines this tolerance.
So this was the context of my question. Now, could you consider having part of the computation done in one rounding mode, and the other part, like the verification, being done in another rounding mode, and how much does it impact your work?
If you're saying the computation is done in one rounding mode and then the accuracy theorem is in a different rounding mode?
Yes.
You would have to account for that in the accuracy theorem. It could be done.
It may make sense. It may not make sense.
I don't see necessarily a reason for it, as long as the rounding in the implementation is in IEEE rounding mode. Like, you can model that in the accuracy theorem itself, but not for stochastic rounding.
Yes. But you also talked about using, you said you used the rounding to nearest in most of your computation, but the very precise specialists in arithmetics, they don't stick to only rounding to nearest.
Oh, they might use something like round to odd instead, but you can include this in your specification as well. Yeah, I mean, we have not, in LA proof, we assume always round to nearest, yeah. But this is also the case for the general accuracy theorems that are given in the textbooks for basic linear algebra. So maybe, like, if you're looking at some very different computations, you might use a different rounding mode. But in the BLAS implementations, they're always using, for the most part, round to nearest. Yeah.
Okay.
With some
maybe
caveats.
we can take this offline.
With some major caveats. Okay. Thank you.
Okay, so our next speaker is Matthew from Bloomberg, who's going to be talking about lowering Rock into C++.
Yeah, so this is a joint work with Jumi, and also I realized this morning that with Ariel, the three of us round out all of Andrew Appel's 2024 students. So we have a theme this morning. So in this room, I think there is one thing that we could all pretty easily agree on, and that is bugs are bad. Maybe there's an alternate argument that could be made because bugs also give us fun problems to study, but at least in code, bugs are bad. And a second thing that shouldn't be too controversial here is testing is great, but it's not enough. So as one example, at Bloomberg, in an implementation of concurrent hash tables, here we see a commit where a bug was found because tests are in particular weak at finding bugs that arise from concurrency, because concurrency results in non-deterministic behavior, and it's impossible to actually test their absence, and thus we need stronger methods if we want to prove or guarantee the absence of bugs in concurrent code. And in this case, this line of code caused a data race where there was two threads trying to access the same location in memory. So, as one solution to this problem, Jumi and I are presenting Crane, which is a new tool where we extract Rock to C++, and our approach is to generate functional style, memory safe, thread safe, and readable C++ code. And also, this is very much still under active development, but we at least have the basics up and running, so we can talk about it. So why did we choose C++? Well, at Bloomberg, C++ is the primary programming language used, and because we actually want to get to the point of having verified code in production, it is kind of makes the most sense to meet engineers where they are and try to work with them instead of imposing as many changes as we might want to theoretically. So it's a pragmatic choice and very practical. Also works with existing code bases. And along those lines, we also strive to generate code that's readable and looks relatively normal, so it's not so scary to the random engineer who maybe doesn't know about Rock or verification. They can still potentially interact with code that was generated by our tool. Also, one thing we learned while developing this is that C++ actually has a relatively large number of functional features, making it a relatively natural target when extracting Rock. But it still is a kind of systems-level language that allows for low-level optimizations when necessary. And so it kind of acts as a portable assembly language, combining the best of both like a low-level language, but also some functional aspects. So it's been kind of a surprisingly nice language to target for Rock. So having said that, what does functional style C++ look like? What is the code that we extract? So to start with, let's look at an inductive data type, lists. So how do we write this or translate this into C++? Well, we end up with this. A lot of code, looks like C++, maybe a bit scary, but if we look at the individual pieces, it actually makes some sense and lines up. So first, let's look at the nil constructor. When extracting C++, all of our constructors become structs in C++. So if we look here, we have a struct that we call nil. It has a template argument, which basically says it's parameterized by some arbitrary C++ type. And this struct doesn't actually contain any data because, as we'd expect from Rock, nil doesn't contain any parameters. But we do associate with it a constructor make, so we can make empty things. And then for the cons constructor, again, we end up with another struct. This time we call it cons. But it actually does contain data. So it contains an element of A, or in this case, really the type that would correspond to what A was. Also has a pointer to another list, and again, a constructor. And lastly, the actual type itself, list, is translated this thing called a variant in C++, which, and if you're not familiar with that, it's really just a coproduct. So the list type is the kind of things that are either nils or cons. And altogether, what we end up with is list is extracted to a relatively normal-looking implementation of a linked list in C++, which is really what it should be. And now, what about a function? How would we extract the map function? Or I guess, do we? Well, again, a relatively more verbose program in C++. But it also carries the same structure as the original Rock code. So looking first at its type, more verbose, but it takes, basically it takes some function from two types that are given as template arguments and a list, and it returns a list of type A and returns a list of type B. So everything is still kind of preserved, relatively speaking, to what it was originally in Rock. And now we have pattern matching as the kind of core structural element of this function. And this is doable in C++. Again, syntactically, it's quite different, but we have this thing called the visit overloaded pattern. And it really does correspond precisely with match. And yeah, so we see visit overloaded, and some stuff we'll go over in a second, and then we apply that thing to our argument L. And yeah, it's the same as a match L. Now looking at each case, the visit overloaded pattern basically takes C++ lambdas, and they act as the case arguments for each branch. And so for the nil branch, nil goes to nil. And if we look at the C++, we have this lambda that takes a nil of type of list A, or a nil A struct, really, and returns the nil B struct, which there's only one because they're empty. And in the case of cons, we have this second lambda that takes some arbitrary cons A struct in C++ and builds a cons B struct by applying f to the argument contained in the cons B struct, the term itself, and then recursively calling the function on the tail of the linked list. So, at first it looks pretty different, but at the same time, we're really able to match the precise syntactic structure modulo very different concrete syntax. Having said all that, we also want the ability to customize extraction and to represent things so they look a bit more natural in C++. So, because we also do this as a fork of the standard OCaml extraction, we kind of take the same approach and allow users of our extractor to provide custom things, like custom ways to extract any term in Rock. So as an example, in Rock, cat is the name of string concatenation. And if we want to, if we end up extracting strings in Rock to strings in C++, we may also then want to change how we represent the string concatenation. And we do that by this command inside of Rock. And if we look at it, we have this %a0, which is just a kind of macro thing that represents the first argument, %a1 that represents the second argument, and then when we actually extract cat of two strings, it'll then become the first string plus the second string in the C++ file. And we can also specify at the end a library where that we may need to import in the file in order for this syntax to work. So in this case, it'll add the import string in the kind of top of the C++ file. And similarly, we also allow users to customize how inductive types are extracted. And in the case of bool, it looks like this, where we provide the name of the type in C++ corresponding to the Rock type. We give the names of the constructors, the representations of the constructors. And also we give the representation of the pattern matching. And in this case, we have to, again, have these macros to account for where all these things are placed. So as we want pattern matching on bools to become if statements in C++, we use an if statement, and we kind of are able to place the scrutiny in the syntax in C++ by %scrut. And we have %br0, which it says where to place the body of the first branch, and %br1, where to place the body of the second branch. And with this, yeah, our bools actually match to C++ bools, and it works out pretty nicely. And lastly, we also provide a way to support monadic effects and extract them in a relatively natural way in C++. Because as most of us know, Rock is a purely functional language, and that means it has no actual effects. So we don't have I/O or state or concurrency. And given my original example, you think we'd probably want to talk about that, and indeed we do. Rock is just functions manipulating values, and in functional programming, we can use monads to represent effectful computation. And indeed, that's doable in Rock, and that's what we do here. And to then support actually having those computations occur in the extracted code, we provide an abstract interface that allows users to specify both the functional interface for their monadic effects, and also then how those things that in the interface are actually represented in the C++ files in extraction. And in our case, we plan on using iTrees to represent all of our effects because they're a very common and useful way to write proofs about effectful code. But that is a choice, and our interface works for any kind of monadic effect itself. So to show how this all works, we'll look at a very simple example we're familiar with, I/O. So when working with I/O in an iTree setting, you first define a type family containing all the operations of the effect. And then to make it into a monad, we derive the actual monadic interface using the iTree infrastructure. And then, when it comes to the extraction side of things, we tell Crane that IO is a monad. And we also specify how each operation should be extracted in C++. Having done all that, we can then write a monadic function inside of Rock, as one would always do, like typical normal. And in extraction, it actually extracts the C++ looking like the function you would expect without any, directly. And yeah, works out quite nicely. So the last thing, we're particularly interested in verifying concurrent code because concurrency is hard. And so why is it hard? In general, there's 3 approaches we're going to talk about with concurrency. If you do fully uncontrolled concurrency, you could have multiple threads accessing the same part of memory, and you could have data races, and it's just very likely to have bugs. And so that's not a particularly good approach. You could use locks. And so when using locks, threads kind of each uniquely claim access to shared memory, which guarantees the lack of data races. But threads can be waiting to get access to a location in memory. You could have states where the code gets stuck because every thread is waiting for some piece of memory and none of them can continue to progress forward. And also, this approach doesn't compose horizontally as you add threads. So our approach that we plan on using is software transactional memory. So in this approach, each thread computes optimistically, and before committing an actual change to shared memory, make sure that nothing else happened that affected the shared memory, and if so, it retries. But with this approach, it's composable, there's no data races, there's no deadlocks, and there's no waiting, which we like, but there's a chance of computation repeating itself because of how it's structured, which is a bad situation. It's not good if you have expensive code in these blocks. It also limits what monadic effects can happen when accessing shared memory. And our goal is to then use this to implement a concurrent hash table using this approach I talked about earlier. So we've implemented an STM library, defined the interface, implemented a hash table with it, and have extracted it already to C++. We have yet to do the verification, but we intend to do so. And quickly, what do we mean by safely? So one thing to make very clear, we have not proven this correct, and we do not plan to. Instead, we plan on using more lightweight methods, such as differential testing our extractor to others that are verified. And also, all of our generated code will undergo the same testing as handwritten code would in production. But this gives us a lot more flexibility to kind of generate code that is useful and kind of acceptable to the engineers that we're working with. And so as future work, we have a lot of things we want to do, including supporting more of Rock, because right now we don't support co-inductive, some of the more complex dependent inductive types. We're midway through implementing modules and some other things. We want to definitely improve the runtime efficiency of extracted code without sacrificing readability too much, which is a bit of a challenge. So our current thought is to do CPS conversion and defunctionalization as a kind of happy middle ground. We'll see how that goes. And in the end, we would love if our extracted code generally runs faster in C++ than using OCaml extraction. So, we'll see if that actually happens, but that's our goal. And also, we want to actually verify code that gets into production at Bloomberg, because that'd be pretty exciting. And so, again, Crane is an extractor from Rock to C++. It's functional style, memory safe, thread safe, readable, and it's not verified, but we're still doing things to ensure its correctness as much as possible. And yeah, we're trying to get it in production, do concurrent stuff. So, thanks for listening.
Time for one quick question as Gregory gets set up.
Great talk, enjoyed it. I wanted to ask, we have the same problem with other kinds of generated code. Once you put your generated code into C++ and now you want to maintain it, how do you do that?
That would be a good thing to talk to you about. I don't have any particular thoughts. I mean, you could change it in Rock, obviously, and then regenerate it. But
If you did it by hand, mightn't you introduce a bug?
indeed, that would be a concern, which is why so changing in Rock would guarantee it, but you'd also have to change proofs. Yeah, it's not so straightforward, but stuff we're looking to solve.
Happy to work with you.
Thanks.
All right, so Gregory will be our next speaker. He'll be talking about some work on specifying and verifying a microhypervisor.
All right. This is work that we worked on while I was at Blue Rock Security with Haidong, and I will be giving the talk. So the context, if you've talked with me over the last 7 years or so, you've probably heard about this crazy project we have. The big ambitious goal is to verify a hypervisor stack. And that's a product that Blue Rock Security has been working on, and I've been working on the verification of it for a while. So this hypervisor stack is a microkernel hypervisor-based system. It works on the Nova microkernel. And user space applications in a microkernel stack, or microkernel architecture, provide the interesting functionality that you would actually think about. So you can think about the microkernel hypervisor, Nova here, is kind of like a hardware abstraction layer. Provides very low-level pieces, similar in the academic community to something like SEL4. So the focus of this talk is about the verification of just this one component. Other work we've done is focused on the verification of these other blue components. We've got some interesting work out about verification of virtual machine monitors and things like that, but in this talk, I'm just going to focus on Nova. So what's a microkernel hypervisor? Microkernels have this philosophy that everything that is not absolutely necessary to be in the trusted computing base can be removed from the kernel. And so what this does is we look at, or I should say, when I say we look at it, the developer of the microkernel hypervisor, Nova, has divided the system resources, which are down here, things like memory, interrupt controllers, and things like that, and exposed them via several APIs. You've got an API to the CPU that provides things like threads. You've got APIs to memory that allow you to control page tables, APIs to interrupts and devices. Okay, and we've done work that gives us a specification for verifying Nova, which is written in C++, and doing verification of those applications on top of it, which are also written in C++. And the nice thing about our approach, so we use separation logic everywhere, is that you basically get the same sort of nice reasoning principles that you would think about, and they're very naturally captured within separation logic. And I'll make a note here, everybody goes, tries as hard as they can to get rid of concurrency. When you do a system like this, concurrency is unavoidable. And it's even worse than you might think, because normally we think about, well, I'm racing with myself, with my own things, so I can maybe put a lock here or something like that. Microkernels and things like this, they race with other hardware, right? So half of what's interacting with page tables is the code that you wrote, and the other half is the MMU, which some Intel engineer or ARM engineer designed. So you don't get a choice on what they do. All right, so at the technical level, verification, we're doing everything in separation logic. So we're starting with an axiomatic semantics of C++. That's this brick program logic that we developed at Blue Rock. And then we do separation logic proofs of the actual C++ code that runs, and the specification of Nova is reflected in C++, in separation logic. And we're using Skylab's separation logic automation to do those proofs automatically as much as we can. On a logistical side, this is a big project. This is 15,000 lines of code or so, very highly concurrent and very subtle and built with a very keen focus on performance. We are focused on the architecture-independent portions of this code at the moment. That's the vast majority of the implementation, and the vast majority of the concurrency portions of it are embedded in that. We've been taking what we call a spike-driven approach, which I'll tell you about now. So one of the features of Nova is fair semaphores. This is their informal documentation, which we've formalized. What we do is we expose the various pieces of this state as separation logic assertions. So here we've got like the counter. The value of the semaphore is exposed as sm.counter of an object and the number. And then we can expose the operations. What does it mean to sem up or sem down? Well, first it means to resolve the selector. You can think about these as like file system handles in an operating system. So you resolve the selector, you check that it is actually a semaphore object, and then you do this increment operation. Each one of these things, so we're saying that this hypercall occurs in two logically atomic steps. The first one is that resolution, and the second one is the increment. Each one of those steps is captured via an iris atomic update. And if people familiar with iris will know what this means, but basically it says we can consume this resource SM counter, we can replace it with this new resource that happens atomically, and then after you've done that, you get to continue with this continuation. That's what gives us the monadic bind. And we can do this for many things. We've done this throughout the entire API of Nova, and so we basically coded Nova in the separation logic. This is something I've gone off on. Like I really enjoy the idea of programming in separation logic and using that as the specification. Works very well, and we can do verification against it. So this is verified in Rock. What does that mean? We've taken these logical specifications, and we've shown that the C++ code that implements them actually takes these steps at the appropriate times and maintains all the other invariants. Now I told you that, this is what it looks like, and it's a little small. Up there in the top left corner, you can see the source code. This is the actual source code of Nova. We made no changes to it at all. This is the specification of that function. This is Coq code, or Rock code, sorry. Then you can see this do up, which you can't really read, I'm certain, is the equivalent of sm.anchor. So it's actually mentioning the specification that we're exposing there. And then this is our iris-based proof. And if you actually looked at these slides in great detail, you would see there's some things that you may not recognize, and those are the Skylab's AI automation, which is doing things like symbolic evaluation of C++ code. Now, when you verify something like a hypervisor, you have to be very careful about what you do. Like I said, this is verified, but that doesn't mean we verified absolutely every single line of every bit of code, because when you execute this thing, you're going to start by running some assembly code, which, we don't have a program logic for assembly, we have a program logic for C++. So when we talk about a spike, what it is that we've done is we've carved out kind of like the interesting control flow that happens at that level. So this is the for semaphores. And we have verified the things in green against specifications of the things in orange, right? And why is it important? Well, if you were to look at like EC unblock, if you were to verify EC unblock, you would need to go and verify the scheduler, which will start which will start executing something else, which will ultimately end up, back in the entire rest of the system. So we've taken various pieces of this and kind of put them out, and what we do is we focus on various functions, we verify them against other specs, and then we kind of push our way down, usually trying to focus on the most interesting stuff where there's concurrency and stuff like that first. This is where we are right now. So there's a lot of stuff that's green. The top level spec is green stuff. This is stuff we've actually verified software running on top of Nova against. We've done a lot of proofs there. The proof column here talks about what we've actually verified within Nova, as well as a bunch of stuff over here. The colors are not great. So this is actually green as well. And you can see that we've kind of where we've been focused on some of our work. So that's the end of the talk. I hope I'm on time. Actually, don't know. So all of Nova is open source. The source code's available here. We've got a project website that is the formal methods at Blue Rock is at the second link. And the brick program logic and is open source. You can take a look at that online. That is now owned by Skylab's AI, where I work now. And the automation that we've developed that is being used in this is also a product of Skylab's. And in all of these things, we're very interested in collaborations, people interested in C++, or just real systems verification. And there's a lot of interesting problems that arise when you do real systems verification at this level. So thank you so much.
Okay, we have time for questions, so Ralph.
Hi, thanks for the update. I'm curious about this automation that you mentioned. So should I think of this as an AI invoking Iris tactics, or like what is the TCP situation for that? Like how does it interact with the rest of Iris? Could you say a bit more about that?
So the automation, this piece of automation that's used here does not leverage any AI. Skylab's AI is building AI agents that use this automation, but the use of AI doesn't impact the TCP at all. So this is reflective cock tactics or ROC tactics that generate proof terms.
Cool, thanks.
More questions? I guess I have one. So is the dream here to maybe integrate those AI agents to help automate these proofs using the automation you have?
Absolutely, yeah. Yeah, and we've seen some kind of interesting results on this. Like if you think about many of the things that you do in verification are relatively easy. And then you have that one loop that you have to write a loop invariant for or things like that. We found that actually AI agents are pretty good at some of these things. And you think about this in like the context of like abstract interpretation. We have very good theory around much of it. And then there's this kind of questionable part about like widening and narrowing and stuff like that. And I think this is a place where agents can use a lot of data to give good answers there very heuristically and not enlarge the TCB in any way.
Very good.
All right.
Any more questions?
All right. Thank you.
Let's thank the speaker again.
Je dois juste...
Okay, without further ado, and hopefully any more technical difficulties, our next speaker will be Awad Ghani, and he'll be talking about this library for real analysis in RocQ. Take it away.
Thank you very much. So, hi, my name is Abdel Ghani. I'm going to present POPL'26, a library for real analysis in RocQ, and the associated searching tools. So the search tool is already available on online. You can try to experiment with it by going to the following URL. So, what's POPL'26? POPL'26 is the translation in RocQ of the all-light multivariate library. This library consists of more than 20,000 theorems in real analysis, but also in other fields like complex analysis, complex line integrals, group theory, vectors, and so on. And most importantly, this theory, or all those theorems have been checked for correctness in RocQ, and most of them are usable out of the box simply by installing the POPL'26 OPAM library and importing it using the import require directive in any RocQ development. Please refer. So you can refer to the GitHub page of POPL'26 for specific instructions. So how did we obtain this POPL'26 library? So as I said, it's a translation from all-light into POC or into RocQ, and the translation has been made using or leveraging the LambdaPy logical framework. So it has been made in 2 steps. First, all-light OCAM files have been translated into LambdaPy using a tool called all2deka. So all2deka translates from all-light to LambdaPy, and second step, we translate from LambdaPy into RocQ using the LambdaPy export tools. However, when exporting directly from all-light to RocQ, the obtained files use the types of all-light, like num and real in this example. So this won't work directly in RocQ. So in order to make it work natively, we need to add a new step, which is aligning the types and functions of all-light on the types and functions of the RocQ standard library. So we use the notion of alignment, and we obtain files that are natively usable in RocQ. So you can refer to the paper of Frederick on POPL'25 for further details on the process. So what is an alignment? An alignment is simply a kind of mapping between the items in the source logic and their counterparts in the target logic. Here, between types and functions in all-light and RocQ. And as I said before, most of the theorems are usable out of the box, but not all of them. So these are specifically the types and functions that have been aligned into RocQ standard library. And moreover, because in all-light types and functions are axiomatized, we've been able to include in the alignment proofs that the target logic concepts satisfy indeed the corresponding axioms of the counterpart in all-light. Okay, so now we have this big library that essentially and up to now consists of RocQ files translated from all-light, but work is in progress to translate more libraries coming from different logics and targeting various provers, such as Lean, for instance. Work is in progress. And so we obtained this library, which is heterogeneous, and we want to allow the user to send queries in order to look for a particular definition or to look for a theorem according to a given pattern. So the first step is to index the LambdaPy files, as LambdaPy serves as the pivot language, and keep alignment with the target languages or provers. However, indexing the logical framework files introduce new challenges. For instance, the translation to LambdaPy introduces new encoding symbols, for instance, EL and fun. However, we don't want the user to bother with these encoding symbols, and we want him to type his query as, for instance, a theorem using a function that goes from real to num without bothering with the encoding symbols. So we have, in some sort, get rid of these encoding symbols. And the second challenge is that when a user looks for a theorem that uses a function from real to num, it also looks for the theorems that use the function that goes from R to N, because these types are equivalent in the corpus of theorems. In order to address these challenges, we leverage the LambdaPy rewriting engine, and we introduce new rewriting rules. So the first set of rewriting rules simply throws away the encoding symbols, and the second set of rewriting rules aligns everything or rewrites everything, all the theorems and all the definitions into one target encoding. So the search engine also features a query language. The query language, with the query language, one can write atomic queries that look for patterns in scope or scope part of the theorem, like the conclusion, the hypothesis, the name, and so on. But also the query language allows to write more complex queries by combining atomic queries using the injection and the filtering operators. So there is an example of a query that has been submitted to the search query. For instance, we look for a theorem about rearranging elements of a series in real, and we choose to write the query in the following form. We look for a theorem that uses a function from num to num in its hypothesis, but also uses at some part of the hypothesis also the type R. And you can see in the results of the query that the search tool shows the full path of the theorem, including, of course, its name and its exact location. A brief explanation why the theorem has been selected as a result of the search, and both the LambdaPy form and most importantly the RocQ translation of the theorem, so that to allow RocQ users to read the theorem in their native language. So this is a second example that is a little bit more complicated and that combines both the disjunction and conjunction operators over 3 different atomic queries. So to summarize, we compare our tool to 3 different tools in the search tools in the ROCQ community. The integrated ROCQ search commands, the shallow ROCQ search tool, and the lemmasearch.com online search tool. So as you can see that our LP search tool uses a rich query language that allows scope patterns. It's available online, so you don't need to require the libraries in your development before searching for a theorem. And it's most importantly allows to index and search in heterogeneous libraries. So as future work, we intend to index more high whole-light libraries. Specifically, the logic whole-light library have been translated recently into ROCQ, and alignments are available. And so the next step would be, of course, to index them and add them to the library. We want to make our search tool available also on different popular integrated development environments such as VS Code and Emacs. And we want to extend the whole work of translating and indexing libraries to other provers. So work is in progress to target the lean language. Yep, that's all. Thank you very much.
Okay, we have time for 1 or 2 questions.
There is no such thing as a num type in the practice in ROCQ just now. So in the examples where you showed a search with num arrow num, would it make sense to have n arrow n instead, or nat arrow nat?
Okay, so you're talking about this query maybe? No?
No, the after that.
Ah.
Yeah, this one.
Yeah.
You wrote hype num arrow num, but
yes,
this is not something that somebody who is a trained user of ROCQ and not aware of the other systems would write.
Exactly, yes. And so this is exactly why I talked about aligning everything on a particular encoding, regardless of the. For instance, when you look for num around num, it also looks, the tool automatically looks for.
Okay, you already explained it. I must have been distracted.
No problem.
Are there any more questions?
Thanks for the great talk. I'm actually looking at the source code right now, impressive work. I'm just a bit curious because so it seems like the type is like, it's not the usual type that's used in ROCQ, that's in the source code. It's like type with a little thingy, and I saw the definition. It seems like it assumes like type are inhabited. So is that like because it's from HOL, or like?
Yeah, so the type here, actually I'm not quite sure what because I took the definition really in a random way, so I don't know what type means here exactly, but I guess yes, it's kind of defined.
Yes, it's part of the meaning.
Of
yes.
what?
Part of the meaning of types in HOL.
Oh, right, okay. I'm not familiar with HOL. Okay,
Yeah.
thank you.
Exactly.
Okay, well, let's thank our speaker one last time.
Thank you very much.
So now it's time for a short break, and then after that, we'll have the ROCQ developer session.
Okay, test. Yes. So welcome to the second session of the RocqPL workshop. We have planned a 45-minute session with the Rock developers, and in particular, we'll begin with a talk by Mathieu Sozo presenting the latest news about Rock. So that should take about half of this time, so maybe 25 minutes, and then we'll have about 20 minutes to discuss with Mathieu and with the Rock developers.
Cool. It's working, right? Great. Welcome to this session. I posted the slides just now on Zulip. If you want to follow, I'm probably going to skip a bit. I wanted to do a demo and just 5 minutes of presentation, but there has been so much things that I needed to expose or advertise that it's going to take a little more time. In the Q&A, Gaëtan and Yann will be there, but other people can answer questions as well. Pretty simple outline. I'm going to give you news about the last year, what's going to happen in 2026, and some more things about the Rock's future. So some news. In March, we released 9.0 and finished the renaming, implemented a new identity and website. Here's our new logo. I see an elephant, you might see a bird. The release manager was Pierre-Marie. I barely helped. There was also a new website on which you can add information about what you're doing as well, or add documentation about stuff you're doing. I'm going to go into that a bit later. We did a split of the RocqStdlib into two libraries, a core library that's just the things that are necessary to run tactics that are shipped with Rock, and the stdlib, which actually wraps over core lib so that you don't have compatibility issues. And in Rock 9.0, sorry, you also have a single Rock binary that dispatches to the various tools. The system that was implemented by Gaëtan. You can look at the full changelog. We found a few inconsistencies this year related to the guard checker. So propositional extensionality striked again. There was a correctness and completeness issue of the guard checker that were fixed. And not new, but difficult to deal with kind of problem appeared with delta resolvers, which is the way to quotient module passes when you have functor applications and you want to have things be equivalent for the user. You need to basically implement this quotient everywhere in the code, and that was not done correctly. Pierre-Marie can tell you about it and rant about it endlessly. You can also look at the full changelog for this. This was backported to 9.0, but it's also part of 9.1, which was released in September. And the release manager was Gaëtan, helped with Pierre-Marie. Notable changes is the new third polymorphism stuff we did. We changed a bit the syntax and some improvements of LTAC2. You can now write refine in a definition. So lemma and definition are going to be merged. You can make Rock relocatable, which is great for installation issues, portability. And extraction actually now handles third polymorphic definitions. Some new resources that appeared this year. That's a very complete documentation of the Docker setup you can use for CI and CD that was written by Eric Martin-Dorel, who sadly left the Docker Rock organization to move to industry, but we have someone else to maintain this part of the ecosystem. You can look at the paper. It's useful for users and for maintainers of this setup. We introduced platform documentation thanks to Thomas Lamiot, who spearheaded this project. The idea is to have tutorials to introduce some particular tools, like equations, for example, on the website, and that's really geared towards new users that want to learn about some things. It's not a reference manual. The idea is to introduce to the system, and of course it welcomes contributions on all kinds of libraries that you might have or tools. New books were released, Security Foundations, which was just released by Katalin, who's here, I think, yes. which is great. So it's the 7th volume of the Software Foundations. There's also lecture notes from Gert Smolka, which are in construction, but it's already 400 pages, which are really interesting to look at. Social media. We finally said goodbye to Coq Club, which was closed in November, and we encourage everyone who was on it to either subscribe to the Discourse or the Zulip, or both. Zulip is really the most active social place where we discuss development and answer questions from users and so on. Both have email interfaces. In particular, Discourse should give you approximately the same kind of interaction you had with Coq Club, where some people also ask general questions about the system or even the theory on Discourse. This is also replicated on Zulip, so we have we can see the discussion everywhere. And there's a Mastodon account. Just to give you an idea of the state of the Rock teams, we have the core Rock team, 11 researchers and engineers led by a coordinator. So it was Gérard Huguette at the beginning, then Christine Paulin, then Hugo Abelin and me for the last 10 years. We have a set of Rock maintainers of the RocqPL project, so projects in the organization on GitHub. That's about 50 people. There's a Rock consortium that's backed by INRIA and contributors. We have a new contribution from Google this year, I think, that supports 2 engineers, Gaëtan Gilbert, who's really working on the core system, and Sylvain Bourgogneau, who just started maintaining the Rock platform and now is the new maintainer for Docker Rock. Finally, there's the Rock community on which you can contribute packages, which has many interesting contributions. Okay, a little teaser about this year. We should have branched before POPL', but we didn't. So it's going to happen in the coming weeks. So what's new? The scheme command is now provide a more robust way to look up schemes, depending not just on a name encoding of what scheme you want for which inductive and so on. And relatedly to inductive, there's also the integration of eliminators for nested inductive types done right, and you'll see that this afternoon Tom Malamio is going to present this work. Especially for this subject, there's a feedback channel on Zulip for the design of the eliminators for nested inductive types. There is support for sort elimination constraints that was presented by Johan at POPL'. Thanks to this sort polymorphic system, we can now have very generic support for rewriting, where the rewriting tactics just need to have some notion of equality and Leibniz principle for your equality, so that's polymorphic over the sorts. So now you can use rewrite for whatever equality you have, if it's in type, in prop, in sprop. You can introduce your own. There's been also an introduction of automatic goal names for eApply, induction, and destruct. There was a presentation about this at last RocqPL, I think. So the idea is that your goals, instead of having unique identifiers, they correspond to existential variables. So they have a unique identifier, but you can give a name to them. And if you set up the argument of your constants right, they're going to be named after the arguments of your functions, and it's a hierarchical name. So depending on where you are nested in a proof, you will get the right name. So you do induction on a natural number. So the first goal is going to be named O, and the second goal is going to be named S, and so on. Internally, there's cleaner support for abstract and environment extension in proofs. So that required functionalizing a little bit the engine. That's very important for us. Pierre-Marie is very happy about this. So it also means that we are deprecating side effectful tactics like induction and rewrite, which would generate schemes on the fly in an effectful manner. We're deprecating that in favor of a cleaner way. Lots of work has been done on extending the LTAC2 APIs and the notation support to get to the point where it can replace LTAC1. In particular, on the notation side, you can now have custom grammar entries for LTAC2 notations. Some performance improvements were made also to fit with the OCaml 5's runtime. And now, in some cases, it's on par or even improving over the 4.14 performance. Outside of the ROC's core, but in the closed ecosystem, there's been work in LP on determinacy analysis. There was a paper at CPP this year. And you'll see this afternoon I talk about adding a parametricity derivation. More work around the Fresco ERC project, which is a project about formal calculus in ROC. The TROC system, which allows you to do a transfer between different representations of data types, is being extended. There's a talk this afternoon by Thomas. And part of this Fresco ERC project is also the CAPLA language, which is a kind of lower level language to express numerical algorithms. And the idea of the whole project is just to turn ROC not just into a calculator, but something that can work as a computer algebra system. That's headed by Assia Maboubi and Guillaume Melchion. As a calculator, they are still interested in to run fast computations in ROC. So there's a postdoc, Peyo Bortel, who started actually extending VM compute so that you can bind your computation, your numeric types to GMP, for example, to have strong computation. If you have strong computational needs inside your proof. So this is unverified as it is as of now, but might be verified thanks to CAPLA later. A word about events that's going to happen. So in the summer, there's going to be a lot of things. There's an IRIS workshop, so that's of course related to ROC at the beginning of June. There is at Institut Pascal in Orsay a gathering on formal mathematics and proof systems interoperability, and there will be a hackathon in the first week about computation in ROC in particular. We will organize a ROC and Share outside of France for the first time at in Lausanne, so close by. Still speaking French. Thanks to Clément Pitt-Claudel for helping us organize this, end of June. The workshop is going to be co-located with Flock. I don't know the date exactly as of now. And there will be a Fresco summer school in Mexico this summer. So some words about ROC's future and the various research and developments that are done around ROC. So if you've been at POPL', you've probably seen Johan's talk about subpolymerase fusion with elimination constraint. It's partly being merged in 9.2, which will come out, but not entirely. Still, we already have the ability to write generic eliminators and in general generic series over prop as prop type, but also sorts that you might introduce, or you might want to do a development that's agnostic about the sort you're working in. And this afternoon I will talk about a big change to the system, which is universe level polymorphism, to generalize it so that you can really use universe polymorphism in large development. As it is now, it's been very limited. And the change is that we're going to have algebraic universes everywhere, and it's relying on a new and verified constraint satisfaction algorithm. If you've been at POPL' as well, you might have heard about rewrite rules. There's been work by Theo Winterhalter and Jan Leray on extending the definitional equality of ROC with arbitrary rewrite rules. So subject to some constraints to ensure subject reduction, for example, or normalization. So we don't have all the safeguards yet, but you can still play with the system. In particular, this allows you to work up to associative and neutral operations definitionally. So, for example, if you index your vectors by numbers, you can have the usual associativity and neutrality rules for free. so it can avoid some dependent type hassles. And the main idea that they put out is to be able to abstract over encoding. So we're thinking of using this to provide a nicer interface for example, equation styles or dependent pattern matching encodings. So you don't see the encoding, you get the nice rewrite rules that you would get. I mean, basically having the same definitional equalities you would have in Agda for your definitions. But you can, I mean, play with this to also have sigma calculus, so substitution and renaming primitives be done by rewrite rules on your TAME language that would be deeply embedded in the system, so that you don't need to reason about this anymore. Or actually, you can enjoy more computation on that part. And it also allows you to model axiomatic quotients just the same as it was done in Lean. A big change that might happen in the future is the ability to work in observational type theory. So this idea of third polymorphism that we introduced is actually also meant to allow experiments with a new theories by introducing a new global sort with some particular properties different from the existing ones. And in observational type theory, you move from Leibniz equality in prop to a proof-errant equality in S-prop, where equality is defined on a type-by-type basis. You have UIP built in because it's in S-prop. You get functional and extensional and propositional extensionality by definition, and quotients by propositional relations are done without breaking the meta theory. The nice things about OTT is that it still provides axiomatic freedom in the sense that you can add any consistent axiom in S-prop without breaking computation in type, which is quite different from usual hot homotopy type theory. Okay. Another different sort that we might introduce is a ghost sort or erase sort. This is work that was initiated by Theo Winterhalter that we are looking to pursue. And the idea here is to have a sort for proof irrelevant and computationally irrelevant data. So basically ghost data that you still want to be able to reason about, that your ghost natural numbers have no confusion, and so on. But still ensure by typing that this does not influence the computations that you do in type. And you can erase this at extraction time, or even as Theo was proposing at conversion time. Which this work is inspired, of course, by a lot of previous work on implicit calculus of constructions, or even grading in series like Agda and Idris. If you've been at POPL, again, you maybe have seen the very nice talk by Nathanael Koura. In work with Xavier Leroy, they propose a new conversion algorithm implementation that is lazy and concurrent and provides a kind of optimal conversion checking with sharing. And we are looking for someone to help Nathanael implement it in work as a new variant of conversion. There's also a lot of thinking right now about that actually comes from talking to users of the system, where controlling reduction and conversion is a very important matter. It can be blocking for some developments when at your QED time you just don't know if your problem is going to be, I mean, your type checking problem is actually solvable in a reasonable time. So there's been proposals and actually implementations and prototypes for fine-grained subterm selection and reduction strategies when you want to reduce just some particular part of your term. It's also useful for teaching purposes. We have no tactics that allows you to do a single beta reduction in work. After 40 years, it's a bit strange. Yeah, there are also thoughts about adding some kind of traces to the conversion algorithm to avoid this dreaded QED that never ends. Other projects around ROCQ in the larger community, I would say. There's 9R in France, so it's a small research project gathering a few people on OCaml for ROCQ, or ROCQ for OCaml, I don't know how to say it. You can talk to Gabriel Scherer and Pierre-Marie Pedro about this. The idea is to tailor OCaml to ROCQ's need, runtime needs, for example, or representation needs. There's a PhD thesis that started so Mathis Bouvreau-Dupuis, who here started a PhD thesis on bringing up the meta-programming that we have in MetaRock to a new level where you could actually verify your meta-programs. It might not be based on MetaRock exactly in the end, but that's the idea of the thesis. And we're working also on formalizations of this sort poly and elimination constraint in MetaRock, and work also on the guard condition, formalizing the guard condition. On verified extraction, so you've probably heard about this project Certicoq, which allows to compile Galena programs to C programs in a verified way. There's been many works following that in the recent years. There's a WASM backend to Certicoq that's verified with respect to the formal specification of WebAssembly. Together with Yannick and Nicolas, we also verified we verified compilation to malfunction and also verified a separate compilation theorem. And there's been work by Jumi, Catherine Stark, and Andrew Apple on an FFI, a verified FFI for C, so you can write your program in Galena, and relying on some functions that are actually implemented in C and get specifications for this C implementations that allow you to link them safely with generated work code from Certicoq. So we are trying to gather this project in the Peregrine project, which is a new project that us at INRIA, people from Aarhus University, from IOG, so it's a blockchain thingy in Agda, where people are working in Agda, and also Ethereum people, to use the Lambda box middle end of MetaRock to actually have a full compilation from Rock, Agda, and Lean to Steelite, WebAssembly, Rust, and CakeML. The red parts are unverified, and the green parts are verified compilation chains. There are two elephants in the room, so the Rock logo, but also AI. There's work at INRIA on using LLMs for coding and also for proof assistance and math. And maybe you've seen on Zulip yesterday, Jason posted a translation from the Software Foundations Volume 1, I think, from Rock to Lean, plus thanks to a Lean importer that was written by Gaetan, you can look at the generated Lean code, translate it back to Rock, and prove an isomorphism between the original code and the back translated code, which is done by an LLM, except for six proofs, and it's 700,000 lines of code. That's it for me. Let's go to the Q&A.
Okay, so I think we have a lot of time for questions.
Okay, I'll let them sit up. No. Okay, so hey.
Hello.
That's a lot of very cool things. I was wondering what the plan is for core lib, and especially with all the changes to like universes and schemes and whatnot. I guess there will be some sort of a rehaul of core lib to integrate all of these things and hopefully help the other people building on it to also use these things. What's the plan there?
Do you want to answer? Or the introduction of core lib, maybe?
You are the expert on the new Prelude stuff, I think.
Okay. So actually, the whole work we did on sort poly was already, the first paper on sort poly actually introduced a new prelude that was using the sort polymorphism stuff. We did not try yet to rebase, for example, the new stdlib that's been split on top of this and see what compatibility issues we might find. but regarding less intrusive changes like the schemes and so on, we, as far as I remember, the features were done in the most conservative way to not break existing developments, as is usual. But I will talk about it this afternoon a little bit, but with the new, once we have the algebraic universes as well, we can really think of making all the core lib very generic, and in that case do the rehauling, and that will probably be a major version for which there will be more difficulties translating, but by that time, AI stuff will be solving our problems.
I was going to ask if we can help, but then yeah, we don't need to. So don't. Okay.
We'll see. We'll see.
Thanks.
Hi, I have a question about this stdlib split. So no idea if the right people for that are even here. So it seems like there's no longer a one-to-one mapping between ROQ versions and stdlib versions. And I was wondering what the plan for that is, because I'm slightly concerned of a testing matrix of an end-to-end mapping where we have to check iris against combinatorial explosions of combinations of ROQ versions and stdlib versions. So I was wondering if you had any thoughts on that, or if there were plans to maybe avoid having to test such a combinatorial explosion by having a one-to-n mapping, or like whatever the plans are there, because currently it's all very unclear to me.
Mm-hmm. I guess it's for me again, because Pierrot is not here. So Pierrot implemented this split. So right now, right now it's nicer because the stdlib did not change between 9.0 and 9.1 yet, and I don't expect it will change between.
There has not been a new release since 9.0 for the stdlib, and I don't know when there will be. So currently there is no explosion.
Right, but I mean,
but
like if there is then an stdlib like 9.2, but it supports all ROQ versions from 9.0 to 9.2, now we start to have a matrix of things we have to test, or we just have to hope it's sufficiently compatible, right? So I would hope we could maybe avoid that matrix, but I don't it would just be good to know what the plans are there, because right now as a maintainer of a widely used library, it's a bit uncertain what we expected, what would come towards us there, and it would be nice to avoid having to test many combinations.
Yeah, I think the goal will be to maintain as much as possible.
It's like any other dependency. You decide what your combinations you support, and then you test those.
That has a problem of fracturing the ecosystem if different big libraries make different choices for that dependency. So like the standard library is usually not just every other dependency in most languages, and there's a good reason for that.
I would like to continue this discussion on libraries. Right now, the objective of separating a standard library was to make it easier to add new elements in it. So in the beginning, it's mostly about preserving compatibility with past versions. So we'll see when there are changes that are breaking compatibility. But let's learn by when advancing.
So I was wondering on sort of the topic of expanding the standard library, like, I don't know, from my perspective, it would be really nice to have like a lot of the stuff from, the standard library ++ in the standard library itself, and that there's a fair amount that is, missing that I would want to see in a standard library for ROQ. Do you have thoughts of moving in that direction?
Yes. Cyril, please.
Okay, so I'm not representing the development team by saying what I'm going to say, but I don't think it's a general problem that many people have, because there is not one single extension of the standard library that people are using. Some people are relying on math components, some people are using an STDPP, some people are using the TLC. There are so many extensions to the standard library, so I think the general project should be to try and merge all of these into a single library that would support all those uses. And unfortunately, there is no single feature that all those libraries are using. Some are using type classes, some are using canonical structures, some are, people who rely on the same features in the standard library actually use modules instead of any of those and treat the instantiation manually. And so I think the way to go is to have another a language that generates all those descriptions in one go, so that you can use them as you want rather than having to commit to a particular way of using structures, because depending on what you're doing, you want to package things, you don't want to package them, you want to rely on one mechanism or another. So I think there is a lot of work, but neither of the current solution is the one that should be a default somehow.
Okay. Oh.
So I know in 2025 there was a lot of talk about things like editors and editor support, and there was markedly less in this discussion, and I'm wondering
yes.
about the infrastructure, Dune and RocqLSP and VS-ROC2 and things like this, and if there are plans in the ecosystem for that, or if they're looking for maintainers or that sort of stuff.
Okay. I carefully avoided that slide, indeed. So indeed, we still have the two LSPs that have been developed that are used in VS Code, but also Emacs, and probably in Vim. I think there's also people using that. And RocqID is still being developed. We have Emilio, who was maintaining RocqLSP, who moved to the Lean FRO in December. So he will no longer maintain this part. The goal is to move this to Rock community and find maintainers. We have all the people that can help at least just maintain the software, and probably merge this functionality with the other LSP developed initially by Maxime Denès and now by Enrico Tassi and Romain Tetley, who was an engineer at INRIA, but he moved to a higher positions, and now he's trying to build a team of INRIA engineers that would know the code of the LSP and be able to participate on it. But not just one person that might move, but a team that could do code sprints on one way to implement a feature. We are actively looking. It's like the most pressing issue, of course, to have a good plan for the coming year on maintenance of this subject. As you were telling me, there are also experts on this kind of infrastructure stuff in companies like Rodolphe Lepig, who was part of the community before joining you, that we are looking forward to talk to and work with to solve that issue.
We still have about 10 minutes. Are there more? Yes.
Hi, excuse me. I apologize if you already answered this. I came in a bit later. As a relatively new Rock user, sometimes the error messages are actually quite good and really informative, and sometimes maybe not. I'm curious if you're looking at all in the current versions or in future versions of different or newer error message communicating, or if you think they're going to stay relatively the same as to what they are now.
I think we want to improve the error messages, but it's hard, and we really need people to tell us this specific error message is not satisfying, so that we have something specific to look at sometimes. So, for instance, I tried looking at syntax error messages, but I don't have good test cases to see if what I'm doing is really an improvement, so it's hard to progress. So that kind of thing.
Okay, when we find error messages that we think could use improvement and maybe would be possible to fix? What's a good way to communicate that?
You can open an issue on GitHub, or you can open a thread on the lib, which may feel a bit more lightweight to you, or any other communication channel works.
Okay, thanks.
And not just for error messages, for anything you think could be improved, even if you're not sure what the improvement would look like. Just tell us, and the worst case, we will ignore you. Don't worry about making a nice message. Just say this thing is kind of weird, and then if we ignore you, you haven't wasted your time. And if we think it's interesting, you can write more later.
So we have a habit of tagging issues on the site, and some of them are just tagged as wish lists. So you see, you have a broad choice of impact you can have with the remarks you make, but communication is really important. So.
Is there a rough rule of thumb for roughly how much after a ROCq release the corresponding platform version comes out?
So Sylvain is not here, but we're hopeful that we are going to have the 9.0 platform released this month, and so you have to understand the scripts and how it works and how to deal with packages whose release for some reason does not work on Windows. But he was really hopeful to have a document explaining all the steps he needed to take and be able to release in 1 month or 2 months after the release the next platform. Yeah. So it should be a lot faster now. I mean, the coming year.
The last time I discussed with Sylvain and David Marjorie, they were signing the packages.
Yeah.
So it's really hot now. We have to, on a strategic point of view, we have to understand whether sometimes we are delayed by the fact that some of the packages, which may not be used by a lot of people, have an awkward compilation process, and for this we may take 6 weeks or 2 months to find a solution to make it work on all platforms. And so somehow it feels that maybe it's not optimal to try to do this kind of release where you make the promise that everything is going to work everywhere, all at once. I know, that was a movie, but...
It is a tradition at this Q&A session for an Irish person to ask this question, so I can't skip it this year. Are there any updates for the situation of unification in ROCq?
Yes, actually, people are working on it. We have a new expert, a student of Cyril Cohen, is now improving the unification. So Quentin Vermont is improving the unification algorithm. And we have also projects that are ongoing on using Unicoq, a replacement for ivarconf. And I've been talking to a lot of people doing formal verification, and the idea of having at least a way to make apply and rewrite, etc., use an alternative unification algorithm like ivarconf or Unicoq. It should not be very hard to at least provide this possibility. You will get the incompatibilities to fix on your side, but generalizing so that at least you can try, yes, that's top priority, yes.
So this is something that's been bothering me for a long time. So I understand that, like I asked earlier about standard libraries and like sets and so forth can be, like there's a lot of different implementations out there. There are real numbers. Why are there no complex numbers in the standard library? I really want them there.
I don't know. Yves, do you have something to say about this? Yes.
Yes, but it was
An
an answer
answer?
to the previous question, so it's the overlapping questions. That there is also a PhD starting in Paris on unification in Rock.
I guess I have the mic to answer the question about complex number. I guess there is no real answer except that no one did it in the standard library, but there are several implementations in other libraries that do not rely on the standard library. So I mean, that's the curse and benefits of the Rock ecosystem. Many people did it in many ways in different places, and now we have to synthesize at some point.
Hmm.
They all look pretty similar. They're pairs of real
No,
numbers.
then actually they are not in some ways because they don't rely on the same infrastructure and they don't generalize in the same way. For example, the ones in MathCom, they are not complex numbers. They are the algebraic closure of a real closed field. So you can pick the real numbers, but you can also pick other real closed fields. So they are not.
And also from basically like some researchers keep complaining about it. So I'm not quite sure the real numbers in the standard library are the one you actually want to use and the one you want to build complex numbers on top of them. So
But the real numbers are the ones that are included in the Coq standard library. So if you're going to, you might as well have complex numbers that are relying on them, because if you're going to use other reals, then you will have that library installed and you will use those complex.
yeah, I guess that is fair. But then maybe take the real numbers out of the standard library.
It's time to stop, so let's thank Mathieu. Okay, now we continue with 3 regular talks in the rest of this session. just to announce this. Okay, so the next speaker, is it working? The next speaker is Max Kurze, and so there is a title here, and I briefly saw an interesting alternate title, and I'll let Max give the talk.
All right, thanks for the introduction. As you might guess from the title, I'm going today basically report on my experience on working with intrinsically typed languages in Rock. And right, there's another title. If that doesn't say anything to you, then you should just think of this talk as giving you a guide on how you can abuse Rock's type checker to do some type checking of your own DSLs. Okay, so consider this small example. It's just a simple expression over bit vectors. And what we would like to do is we would like to be able to make sure that certain subterms here actually have the same type. For example, because this addition over bit vectors is just defined on bit vectors that actually have the same length. Or we would actually also like to be sure that all the variable references are actually scoped correctly. But before we can get into that interesting stuff, we first have to define this language. And we define this language in a deeply embedded style, like you've seen it probably thousands of times. We just have an inductive, call that action here, but just expressions. And then we have one constructor for each of our language constructs. So we have constants, as you've already seen, but just imagine there may also be not only these bit vector literals, but there may be structs or enums or whatever. So we're a bit more general here. Then we have variables and we have binders. And then to have some more interesting operations, we'll also have addition over bit vectors and we have concatenation. Now, in order to do anything at all with Rock's type checker, we first of all need to encode the necessary information for that in some type in Rock. So we want to do the type checking of our DSL here with the type checker of Rock. We first of all have to encode all the typing rules, the whole type system basically, in the dependent types of this AST. So what we're going to do is we're going to add a new type parameter here, and then we're going to define for each of our language constructs which type it returns. So for the constants, that's just the type of the value. For the variable, we might ignore that for the moment. For the binder, we just forward the type of the body as the type of the whole construct. And then for the addition, we would like to be a bit more specific. So for the addition, we only define this to be well defined if we have two operands that are actually bit vectors and they have to have the same length. And then for the concatenation, they actually might have a different length, but then the return type will actually have their combined length. And now, to also resolve the variable case, we introduce another type argument, and that's, we call it a variable context, but it's just a list of all the identifiers that are currently in scope together with the type that has been bound to the identifier. So for the variable, what we will then do, we just take this variable context from the type level and we force each variable reference to carry a proof that its identifier is actually part of that context. And then we can simply take the type that has been in the context and use that as the type of our variable reference statement. And the other place where the variable context gets interesting is in the binding construct. There we will again take it from the type, and now we will add the newly bound identifier to it before we push it into the body, or in the subterm that we call body. In all other places, we just simply take always the context from the type level and push it in all to the subterms without any modification. Okay, so now that's our language. Let's have a look at a couple of examples. The first example is just simple addition over bit vectors. There's no problem at all. Rock simply type checks this term, but I would actually like to emphasize what it means. That does not only mean that this term is well defined, like the AST is well defined with regard to Rock's type system, but it also means that the type of our DSL that is represented by this AST is actually well typed with regard to our previously defined type system, the one I've just seen on the last slide. All right. A second example involving a binder that we'll also go through immediately without any modifications. And once we have a third example that also has a variable reference, we will actually notice the first problem because RocQ is not able to infer automatically this kind of proof that the variable reference or the identifier A is actually part of the variable context. So we need to help RocQ a little here by providing a tactic that would just resolve this proof. And once we provide the tactic, that example actually works out fine. So far so good. Now if we just take the exact same example and only modify it slightly by adding another binder that's not even used, it's just there, we actually reach another problem. But this time the error message is a bit more weird, or it's a bit harder to understand, because this time RocQ actually complains that it's not able to unify the type that it inferred for the variable reference with the type that it was expecting there. And in order to find out how it came to this error, how that happened to be, we have to have a closer look at how RocQ type checks this term. All right, so here you can see the same term again, just spread out a bit into a tree-like structure. And now I will actually go through step by step on how RocQ traverses this term in order to figure out if it actually type checks or if it doesn't. And RocQ does this in a bottom-up fashion. So you can think of it like RocQ basically starts at the uppermost term and it first traverses into the leftmost subterm until it reaches the leaf basically, and then it will try to infer the type of this leaf on its own without considering any of the environment. So in this case, for the constant, it will figure out that it has no knowledge whatsoever about the variable context, but it knows that the return type here is bit vector of length 2. And only after that, RocQ will actually check if the type that it inferred matches the type that it was expecting on the one level higher, the argument of the bind here. In this case, they just unify, everything works out, and RocQ can continue. We'll then continue to again traverse this tree until it reaches the leftmost subterm, the next one, and infer the type of the second constant, which is again similar as the first one, only that this time it's bits of length 3, and then RocQ will unify the type that it inferred again with the type that it was expecting. Works out again, and now we will eventually reach the variable reference, where it will not really work out because during the inference of the variable reference, the L tag will actually be triggered, and now the L tag sees as a goal that it should just prove that A is somewhere in this extensional variable. And what the tactic will obviously do will just apply ineq and basically resolve our variable reference in something that is not really compatible with the type that we're expecting here. And so it happened to be that these types are resolved to some types that are incompatible, and we cannot make progress anymore at this point. Right. Now, that's a bit of a bummer. Let's take a step back and try to figure out what we would have wanted instead to happen. What we intended to have here is we would have wanted that the variable context is taken from the top level type annotation, and it should be traversed, or it should be passed downwards through the AST, starting at the top and then just propagating downwards, adding all the variable identifiers. So logically, conceptually, the variable references or the variable context should be propagated top down, while the type checking actually happens bottom up. So there's some kind of misalignment there. And the key insight of our paper was that you can effectively reverse the type checking order of RocQ by using bidirectionality hints. So what we are doing is we place these bidirectionality hints in front of all the arguments for our constructors. There's actually one line missing. We also do that for the const case. So also for the constants, we do the same kind of bidirectionality hint. And what then happens is the following. Let's do the type checking again. We again start at the outermost term. But this time, we do not directly traverse into the subterms, but we will first, because of the bidirectionality hint, we will force to first unify with the expectation that we have of the type annotation. Right. And only afterwards, we will actually traverse into the first subterm, where again the same thing happens. We will not directly infer the type of this term, but we'll first have to unify with the expectation, right? So we basically propagate the variable context, and only then the type inference happens. Same thing for the second subterm, so the inner bind will also first hit the bidirectionality hint. So we'll first propagate our variable context. So at this point, the A is actually properly propagated here, and only then the type checking will continue with the subterms. So we just type the const on the left, and then once we reach the variable reference, now the actually important point here is that the bidirectionality hint is in front of our argument h. So what will happen is the bidirectionality hint forces the unification with the expected type, which will propagate the variable context, and then only afterwards the L tag will be triggered and the L tag will be able to construct the proof that we wanted. All right, so now we use bidirectionality hints and everything worked out. Now we were actually able to type check this term and to make sure that all the valuable references in this term are actually correctly scoped. So you might not be excited, you want to go out there, implement this for your own languages, and you will hit certain problems where there were certain terms that actually worked before, but now once we have the bidirectionality hints, they stop working. And that's because it turns out that it's actually quite nice to do the return type unification and inference in a bottom-up manner instead of the top-down manner that we now have for the variable context. So what we actually propose in this paper is to re-reverse the type checking order such that we have two passes. We have a first pass that goes top-down, propagates all the variable context, and then we have a second pass that goes bottom-up again and does all the inference and the unification of the return types for a DSL. But if you're interested in that, then you should definitely read the paper and check out the tutorial that we published. Thanks for your attention.
So just a quick question with respect to the bidirectionality hints. So if I define a ROQ function manipulating the AST, do I also need to add hints?
Yeah.
And
well,
what if I define...
Depends. Yeah. Really depends. If it just wraps... basically, if you're just doing all that stuff, generating the necessary NST, and then you apply it to function, that's totally fine. If you want to apply the function more inside of the AST, then you also have to provide the hints, because then the top level annotation is outside of your function and needs to be propagated through it.
Okay, and what if I define a recursive function? How do you type check the body? Does it work out? Did you try something like this? Or?
How do you mean that?
Because I imagine you can only, I mean, I've never used hints myself, but imagine you can only add the hints after defining a function. Is that the case?
That's fine.
Yeah, but then does it work out, type checking the body of the function?
That's a good question.
Okay, maybe we can talk about it later.
I'm not sure about that.
Yeah, maybe let's take that one offline.
Yeah.
Was there another? Yes.
So last year, someone wrote an explanation for the documentation about bidirectional hints. Maybe that's you. I don't know who's behind the pseudo. And we were basically like looking, wow, that's great. That's how it works. What would be an example of that? So if you have a tutorial, that would be great merging into documentation, because it sounds like a great example of bidirectional hints in real life.
That seems like a really nice idea.
So I didn't quite understand in the end. Maybe you could get us a little spoiler for the rest of the paper. So did you manage to actually make it so that this also works and type checks in current ROQ, or do you more have like a proposal for how ROQ could be extended to make both of them work?
No, it works.
Okay.
We're using basically, there are two approaches on how this can be done. One is, I have a backup slide for that. So one is you can write a wrapper where you're basically deferring the unification of these return types. That way it can work, but you can also get rid of the wrapper and implement it in LTAG2 using the pretype function. Yeah.
Okay, thanks.
Okay, I think we should thank Max now. And the next speaker is Mathis Bouvreau-Dupuis, who will be telling us about sulfur, which is a re-implementation of something like autosubst.
Okay, is the mic working? Okay, so hello everyone. So I'm actually a first-year PhD student in Paris, working with Yannick and François. But today I'll be presenting work I did with Theo, Catherine, and Kenji before my PhD started on Sulfur, which is a ROC library. Okay, so we know since the POPL'26 challenge that a super annoying aspect of formalizing the theory of programming languages and type theories are binders. So when you work on paper, you think of variables and binders as names, and you work up to alpha equivalence. But it turns out alpha equivalence doesn't work super well in Proof Assistant. And you can see if you just, I was curious, and you look at the kind of proposed solutions to the POPL challenge, there's almost as much binder representations as proposed solutions. Yeah, so there has been a lot of work on this. And one such particular piece of work that this talk is based upon is autosubst. So autosubst is also a ROC library developed by many people, including Scheffer, Tebby, Smoker, Catherine Stark, which is a co-author, etc. It has many implementations, and actually many people don't know this, but if you want to use one, it's probably the OCaml version, which is the most feature complete. And it has been used successfully in many formalizations. So quickly, I'll give like a crash course on autosubst. So let's say you want to formalize the meta theory of system F. First step is to write the grammar of types and terms in a format that autosubst understands. You give this to autosubst, and autosubst, well, first generates inductive types representing your grammars of types and terms using De Bruijn indices. Then autosubst will generate a substitution function. For instance, this would be the parallel substitution function, which substitutes all De Bruijn indices at the same time. Autosubst proves basic lemmas about substitution. And finally, and this will be the focus of this talk, autosubst provides a tactic called asimple, which is super useful. And you call asimple, and it basically simplifies your goal using the lemmas it proves about substitution. For instance, you can prove this technical lemma, which comes up when doing, I don't remember, probably the proof of Church-Ross or something like this. And asimple simplifies both sides to the same thing. You do reflexivity, and you're done. So asimple is really very useful. The issue, though, is that asimple is also super slow. For instance, on Theo Winterhalter, which is a co-author, so on his development of the type theory of ghost reflection, asimple takes more than 3/4 of the total type checking time, which is huge. And this is because the implementation of asimple is very naive. That's how it works. It's just a big loop where you do set-to-read rewrite with a bunch of lemmas. And set-to-read rewrite is slow. Putting it in a loop is even slower. Okay, and so the focus of this talk is to present Sulfur, a ROC library, which is essentially a re-implementation of autosubst using different principles so that the asimple tactic can be more efficient. So the interface provided by Sulfur and autosubst are very similar, so I focus on what makes it different, and that's how we implement asimple. Okay. And the key idea to make it faster is not something super new, but it hasn't been done yet, is to use reflection. Okay, so I'll start with a simple example to explain how reflection works. Let's say you want to solve this equation. So here the square bracket syntax means apply a substitution. SID is the identity substitution. So the way you would do this is, let's say you want to use asimple to simplify the right-hand side. This is how it would work. So the first step would be to actually change from this concrete syntax where substitution is a function and identity is a function. You verify it to something where you replace functions with constructors. So it's a different syntax where you've made many things more explicit. For instance, tsubst represents the application of a substitution to a term. SID with a capital is the identity substitution. Then you can write in ROC a simplification function, which translates, which will go from this explicit syntax to itself and does the actual simplification. And then you can translate back using an evaluation function back to the concrete syntax. So that's a high-level point of view, and now I'll go into a bit more details on how these two syntaxes are formed. So the concrete syntax looks like this. So let's say you're formalizing the simply type lambda calculus.
you would have like a constructor for variables, which contains a de Bruijn index. You would have applications and lambda abstractions. You can define substitutions as functions from indices to terms, so a parallel substitution. And then Sulfur will generate, well, Sulfur generates all of this. So you get a substitution function operations, like you can compose substitutions and so on. And then on the other side, you have explicit syntax, which makes a lot more things, well, explicit, it's in the name. So this looks a bit like Sigma calculus with a bit of extensions. So you would have, so in the term constructor, you would have the same thing as the left. So you would have variables, t-var constructor. You would have this t constructor, which kind of subsumes both the app and lambda from the left-hand side. And then you have a bunch more things. You have t-subst, for instance, which represents the explicit application of a substitution to a term. And now substitutions are also verified. So you have a bunch of different cases. You have the identity substitution. You have the explicit composition of substitutions, and so on. So here there's a bunch of things that so here the kind of the TMVAR and SMVAR constructors are a bit special because they represent kind of concrete syntax which we don't know how to verify in the explicit syntax. So we just box them using this concept of meta variable and don't touch them. And also something I won't touch in this talk, but which is present in the implementation, is that we also need to do the same treatment for renamings and for natural numbers. So we need to verify quite a lot of things. Okay. So going into a bit more details, why the concrete syntax is different for each language. So let's say you're formalizing, I don't know, a simply type lambda calculus or a dependent type theory or whatever. Sulfur regenerates the concrete syntax and operations all the time. But the explicit syntax, on the other hand, is defined once and for all, and it's parametrized over a signature. The signature contains the details of the specific language. So it works something like this. So in particular, the T constructor case kind of encapsulates all of the constructors of the base language. So this would be, for instance, application, lambda, etc. And the signature contains a bit of details about the concrete language. It contains the set of constructors, for instance, app and lambda. And for each constructor, the number of arguments and which arguments contain a binder. So essentially, the signature contains the binding structure of the language. Okay. Then just a bit more details on asimple. So the input is a term t in the concrete syntax, and you want to produce a term t prime in the concrete syntax in a proof that both are equal. And the way it works is that you write the verification function from concrete to explicit, and this has to be done using metaprogramming. So in the implementation, I use the Camel plugin. Then you have the other way around evaluation, which goes from explicit to concrete syntax. This is a ROC function. And it takes as input an environment, which is related to meta variables. It contains an assignment from meta variables to concrete terms. And then the nice thing is that since the explicit syntax is simply ROC inductive, you can write the simplification function as a ROC function, and you can prove a soundness theorem for this function. So if you have a term t in explicit syntax, evaluating t or evaluating the simplified version of t gives the same thing. And it's because we can prove this procedure correct once and for all that you get efficiency benefits, because you don't need to build and type check a large proof every time you call asimple. Okay. Another benefit is that since the simplification function is implemented in ROC, it should be quite easy to extend. For instance, the current version is quite naive, but it shouldn't be too difficult to make something a bit more efficient. The kind of the hard parts are the metaprogramming parts, so like the verification function. Okay, so that's kind of how it works. But then future work, so Sulfur is still slightly work in progress. In particular, something we haven't done and we really should do is doing benchmarks. So the performance is noticeably faster than asimple. We just don't know how much. I would guess probably at least 10 times, but we really need to do benchmarks to know. And we still have a couple of basic optimizations to implement. I said the simplification we use is very basic, but we also had some issues with rewrite strat, which maybe we can talk to with the developers afterwards. Okay. Another difficulty, and this one is a bit more fundamental, is that scaling this reification approach to more complex languages is sometimes unclear how to do. For instance, handling multiple sorts in a system F way is not something we support for the moment. So for the moment, Sol4 is more suited to formalizing dependently typed calculi and stuff like this. But it's not clear to do it's not clear what to do in this case. And if you're interested, we can talk afterwards. Another feature we'd like to support is having n-ary applications and in general arbitrary functors in the term syntax. Okay. And then the last direction for future work, more on the theoretical side, is that we would like to have a completeness theorem. Because in fact, in simpler variants of sigma calculus, there is a completeness theorem in this paper by Scheffer, Smoker, and Tebbe, which essentially says that if you have two terms in explicit syntax and the evaluations are the same, then you can join them by simplification. And intuitively, this says that asimple should be enough to decide equality of concrete terms. Unfortunately, this does not hold in our case, and there's some interesting future work here. Okay, so just as a recap, presented Sol4, which is essentially all the subs with efficient simplification, but handling multiple sorts is challenging. Thanks.
Hi, thanks for the talk. Asimple also does a thing, and I'm not sure whether your tool does this, so this is the question. Asimple also does the thing where it looks at the goal and finds all the occurrences of terms and simplifies them all. Do you also walk the entire term to find all the things to simplify? And if yes, how did you implement that?
So in a way, yes, but that's where we had limitations with, so at the moment we use RocqP's rewrite strat mechanism. And this poses some issues because you want to avoid simplifying too much, because if you simplify a term, you don't want to simplify directly its subterms. Otherwise, you're just going to walk terms several times. So it's not clear to me what we want to do here. And if you have ideas, I'm interested.
When you say it's, from an efficiency point of view, is the thing that's slow the actual rewriting, or is the thing that's slow checking the proof term, or is it both?
I don't know yet. We really need to do benchmarks. Yeah.
So, did you guys also look at just an implementation of the repeat first rewrite strat thing? Can you just replace the whole thing with a single call to rewrite strat? Which does term traversal and rewrites everywhere, right?
Compare this directly to rewrite strat?
Yeah, an implementation.
Yeah, that's what we need to do, yeah.
Okay.
Yeah. I still, just a question of time.
So, how hard would it be to hook onto your evaluator to add, for instance, beta equations? Probably you would have to add some few or some sort of easy termination argument, but then you would get an evaluator not just for the substitution calculus, but for beta sigma.
Yeah, so that's what I mean when it's very easy to extend. I think it would be actually really easy to do this. Yeah. So yeah, the only slight difficulty is with respect to termination. For the moment, I've kind of built the simplification function in a way that it's obviously terminating. It's structurally recursive. Not sure that's the way you want to go. Probably you want to use fuel, and then you just don't care about termination. Yeah.
Are you forced to write your syntax in AutoSub style, or can you retrofit it on existing normalizations?
You can use anything. We just chose this for simplicity. We could also choose the format of AutoSubst 1, which is a bit different, more like inline style. Maybe you want to support different things. I don't know.
Okay.
Yeah.
It also reminded me a lot of squiggle EQ. Do you remember? Do you know about this thing that was developed, a kind of generic syntax like this to develop Howe's by simulation relation? I don't remember what it's called right now, but it uses a similar syntax, and there might have been simplification tactic also at the time.
Okay, I'm not
It
too
was from
familiar with
Abhishek
this.
Anand and Vincent Rallier, I think. Yeah, you can look it up.
Okay, we have time for one last question, if there is one. Okay, so let's thank Mathis.
Fabrice is giving the talk.
Okay. Shall I start? Yeah. All right. Hello, everyone. Today I will present about my experience with a technique for performing well-found recursion. I did this in a project with my supervisor, Herman Geuvers, who's not here today. I did this project because 2 years ago at the same conference, Xavier Leroy presented a technique for performing well-founded recursion. As you know, in Roc, all functions must terminate. And this can often be verified syntactically if you only recur on structural subterms. But not all functions are structurally recursive. So one example is quicksort. Very briefly, quicksort, it takes a list and sort it by taking the head as the pivot and then partitioning the tail into those elements that are smaller than pivot and those elements that are greater than pivot, recurring on those two parts and concatenating them. But these sublists less and more are not structural subterms of the list L, and so this definition like this is rejected. And hence we must use well-found recursion in this case. There are multiple ways you could go about this. There exist various plugins like functions and most notably equations. But in this talk I will look at Leroy's method from 2 years ago, which is more manual. I think it's an instructive technique, and so that's why I like to present it. There's two parts to it. First, we're going to define the function and then prove a property about it, and I'll show some practical tips, and this is really a pragmatic guide, you could say. And we'll use quicksort as our running example. So, part one. First, let's briefly recall well-foundedness. So a relation is said to be well-founded if all its elements are accessible under that relation. And accessibility here is defined inductively. So an element is accessible if all R predecessors, where R is the relation, are also accessible. And this is equivalent to saying that there is no infinite descending chains, which intuitively means you can perform induction on this relation because you eventually always reach a base case. And well-founded reduction is, well-founded induction is essentially equivalent to performing structural induction on this proof of accessibility, and you can use the same idea to define recursive functions. So let's go back to our example on quicksort, and we'll start with the naive definition, which, like I said before, is not accepted because less and more are not structural subterms. First, we must determine, of course, why at all this function terminates. It's not that hard to see, because less and more, in this case, never contain the pivot x, so they're strictly smaller. So more precisely, if you would compare these lists by their length, then they would strictly decrease every recursive call. And that's why we'll define the relation on our list as follows. We compare them by length. Next, this is really the crucial step. We add an auxiliary argument here, which is the proof of accessibility of the list L under the relation R. And then in the recursive calls, we must also provide terms for this, of course, and they must be subterms because eventually we want this definition to be structurally recursive in ACK. Leroy suggests to use the inversion lemma arc_inf for this. And since arc is inductively defined, so you can essentially extract the accessibility of smaller elements, and you only need to give a proof here in these holes of the fact that less is indeed smaller than our argument L. And so there's two holes here. There's multiple ways to deal with this. You can provide exact proof terms, but then you know exactly, you need to know exactly what you need to put in. So it's easier to generate obligations for this. You can use refine, but I think program works most nicely. And then, yeah, I mean, it's a trivial remark, but the obligations are defined, so you can clearly see what you need to prove, and this really allows you to follow these steps quite mechanically. In this case, they're very similar, so we can capture them with one lemma here. You can prove it, and then a really nice trick, I think, is to add this lemma to a hints database. Here I'll just add it to core because it's easy. And then our previous definition will be accepted because it tries automation. And this will also be convenient because later we can use this again. And now a nice observation is that this definition is accepted and it is structurally recursive now in the proof of accessibility. We're not done yet, however, because, well, quicksort is a function from a list to a list, and it should not take this accessibility argument, so we need to eliminate it. And this means that we need to provide for every list a proof of accessibility, and this is exactly the definition of well-foundedness. So our last step will be to prove the well-foundedness of a relation and supply it to our function. You can prove well-foundedness from scratch, but it's kind of annoying and tedious. So it's easier, I think, to essentially lift it from the well-foundedness from another known relation. And there's a nice theorem in the standard library called the WF inverse image, which essentially says that if relation S is well-founded, then a relation which compares two elements x, y via S under the image of some function f, then this relation is also well-founded. And in this case, f would be length and S would be the less than relation on natural numbers. And actually this case, I guess, occurs so often that there is a specialization in the standard library as well, which is precisely substitutes the less than relation for S. So that's what we'll use here. We have in one line where we have the well-foundedness of our relation, and then we can fill it in, and we have a nice clean definition of quicksort, which is accepted. So, of course, the next step would be to do something useful with this. So we're going to try to prove a property, and in fact, it's very easy to do so. There's only one catch, I guess. You have to be a bit careful. As I said before, this definition is structurally recursive in ACK, so it might feel tempting to perform induction on ACK. But, well, there's some dependent typing going on, so you run into issues, and this is not really recommended. So instead, you can perform well-founded induction on the original decreasing argument, L. And that is what we'll do here. So first, very simply, state the lemma you would like to prove. In this case, the sorted list contains exactly the same elements as the original list. This is, of course, is not valid because ACK is missing, so we add it. A small detail here. In the proof, eventually, or in the proof, you would like the induction hypothesis to be general over the accessibility, so it's easiest to add it last in the quantification. Then we start the proof by well-founded induction. This gives us the induction principle, and we need to, again, give the well-foundedness we showed before. And we can unroll the function by destructing the accessibility, and now you can continue as usual. At some point, you will, of course, apply the induction hypothesis, and then the goal, most likely, is exactly an obligation as you showed during the definition, because you need to show that the argument you apply the induction hypothesis on is smaller than L, basically. So this is exactly an obligation. And because we added them previously as hints, this lemma, the goal can be just discharged immediately. And so this is a small bit of convenient automation. So we defined a well-founded recursive function using only basic elements, really, without relying on fancy plugins like equations or function. And I would say there's also quite a straightforward design pattern for this. You can follow these steps I laid out. And I especially like adding these obligations as hints and deriving the well-foundedness using a theorem from the standard library. I also made kind of an introductory tutorial for students, and it's available here. And I applied this method on another algorithm on trees with a more specialized relation. So for another example, if you're interested. The method does introduce some boilerplate in the definition because you need to add these accessibility arguments, but I think it's still quite legible. Also, a nice property of this method is that the extraction is really clean because this accessibility argument is in prop, so it disappears completely, and you're basically left with a very clean extraction to OCaml or whatever you like. Another thing I really like about this method is that basically you see everything that's going on. With other methods like equations, there are automatically maybe some wrappers or tupling is happening secretly in the background. You're not really sure, or I am not really sure as a user. But here, really, every step is clear. And I think that's especially useful for students. Like myself, it's a really good way to learn about well-founded recursion, I think. So, thank you.
Questions?
Hey guys, not so much a question, but just to remind you, on the Rock website now there's a page dedicated to tutorials and stuff like that. So if you write a tutorial like this that you think can be useful to a bunch of people, just write a small pull request, we'll merge it, and then it will be on the website, updated with the Rock version, and it will give it more visibility. So don't hesitate doing it.
Want to do something mutually inductive?
That's a great question. That's something I did not look at yet, but that would be interesting future work for sure.
Yeah, thanks for the nice demo. So, if I understood correctly, what happens here, what you mentioned at the end with this auto thing, is that the actual termination argument of like the length is getting smaller, you're kind of reproving this when you're doing the proof. Right, like this auto here redoes the proof that the length is actually decreasing.
Yeah, it basically uses the QS obligation lemma that I defined before.
Right. Which seems a bit odd because we already proved that things are decreasing when we wrote the function. Which, I mean, in your case, so you automated it, so it's fine, right? But in general, maybe this argument is complicated or something. Like it's from a principled perspective, it feels a bit odd that I have to redo that proof. Do you think there's any nice way to avoid that?
I'm not sure because if you perform induction like this, it will be part of the induction hypothesis, and so this, like this, I don't think it's can be avoided.
I mean, I don't know when you do structural induction. I mean, basic structural induction in Rock. If you define your functions, your fixed points structurally inductively, and then you prove your lemmas structurally inductively. It's not like you can follow.
So my understanding is that if you were to do an induction on ACK, then you would get this obligation for free. But since you're doing a separate induction and then a destruct, the destruct gives you the wrong thing, and so you still have to prove the right thing. But it's very easy in both cases. And as you said, the induction on hack doesn't work very well because it's dependent induction, and then everything goes wrong.
This is more a question from Xavier. Would doing inversion of hack allow to get the correct? Would it allow to get the correct term and not have to redo the proof?
I guess the question is, if you can do dependent induction nicely in code, then yes, probably. But it's beyond my abilities of using Rock.
We need to move forward, but during the break you can still discuss this. So now we'll talk about parametricity and the LP, and Wojciech will give the talk.
Thank you for the introduction. I'm happy to be here and be presenting this joint work with Cyril Cohen on implementing parametricity in RocqPL. And what exactly do I mean by implementing parametricity? Well, on paper, parametricity is a property of the type system we're interested in, and it's linked to this relational interpretations of this type theory. And in this talk, I want to assume this point of view where it's not just a theoretical tool for proving things about our type theory, but really a practical tool for code generation, generating theorems and definitions. And how can we do that? Well, in dependent type theory, we have this advantage where relations are kind of a first-class thing because they are really just functions into a universe. So we can implement it as a translation from terms to terms in the same theory. And I prepared a couple examples for what kind of things this CodeGen tool can do. There is this library for doing data type refinement in Coq called RocqPL, which the idea is usually you have this proof-oriented and a computation-oriented data structure, and you're trying to push all of the various computations to the computational part, and then you get a nice theorem that you compute it very similarly to how you would compute in the proof theoretical or a proof-oriented structure. This generalizes to this notion of proof transfer, implemented, for example, in the library Troc, where you don't only transfer computation, but you can also transfer properties. This is a very nice example of what Troc can do, where you have this statement about universally quantified over natural numbers, and you can show that it holds by reducing to a computation in Z mod 9, where you can check just a finite number of cases. And the last example I want to show is generating these displayed objects, which is currently implemented in RocqPL, which allows you to derive dependent versions of your various data types and then use those in your generated inductive principles. And I'm sure that over the past week you've heard many presentations which in the concluding remarks say like, well, and this is probably some sort of parametricity, we're not really sure what the link is. Well then, once they figure out what the link is, they can use this thing. And the way this is usually presented is that we have this translation of contexts, where this is specifically the case of binary parametricity, where a variable in the environment gets translated to 3 variables in the environment, one which shows that the previous ones are related, and then you go on and you translate your terms, and that's all good and nice, but there's this notion of priming of various terms, and it's not entirely clear what this operation does. And now I see that probably the blue background isn't very well visible on the display, so that's not great. It works? Okay, so it's just my angle. Never mind. But it doesn't really help clear up what this priming operation does, right? The essence is that we are running two translations. One is for duplicating variables in the context, and the other is the actual essence of parametricity that we want to get into. And when we are implementing parametricity, we need to care about freshness of variables, which is annoying. We can solve this either by going De Bruyne, or we can handle state manually and pass it around. But we don't really want to, because that's just not great, and it's not obvious that this is something that we should care about from just reading the paper translation. And if we zoom out, we realize that this problem really asks us to handle two things. One is induction on syntax, and the other is nice handling of binders. And in the mainstream metaprogramming frameworks for Rock, such as Occam plugins and MetaRock, we can do induction, because what language now can't do induction, right? But the binders are still pretty manual, and De Bruyne indices are susceptible to subtle errors and whatever. And so it's not great, dare I say, it's a little rocky. And that's why we turn to RocqLP, which stands for Rock, and Embeddable Lambda Prolog Interpreter. And it's a layer on this LP thing, this Lambda Prolog with Rock bindings. And the nice thing it does is that it gives us higher order abstract syntax representation for Rock terms and top-level declarations. So again, I have these two examples, which this part isn't really important. The important part is that the body of the function is represented by a function in LP, which you'll notice that the variables are written on the left of the backslash, but that's something you just get used to. And this holds for both terms, and I also have this inductive data type, where once again, the list of constructors is constructed in a context where it has a variable, an LP variable for the inductive and an LP variable for the parameter. And if you're still not convinced, then well, look at the name, right? It has exactly the two things we need to do. We need to do binders, so we have lambda, and we need to do induction, so we have prolog. So hopefully we're now all convinced that this is the right thing to do. And since now we know that we will be implementing things in a logical language, we will switch from this functional style description to a sequence style description, which you can read more about in the series of papers on Rock. And essentially, we have this judgment that in a parametricity context psi, T is related to T prime because of TR. And T prime and TR are outputs in this judgment. So we have a variable for, we have a rule for the variables, we have a rule for the types, just as before. And I want to particularly focus on this rule for lambdas, where we have the semantics are the same, right? A lambda is related to a lambda because of the translation, which we've already seen. But the way that we conclude this is by first looking for the translation of the type, and then assuming that we have these fresh variables which are related, and we derive that the bodies are related. And this can be very elegantly implemented in LP by this param-Turner predicate. And the way we do it is that each inference rule gets a clause. And we start by writing out the conclusion of the judgment in the clause head and proceed by running the body, which we first implement some sort of naming for pretty printing. That's not really relevant. Then we query the context for the translation of the type, and then we universally quantify over 3 fresh variables, assume that they are related, and then ask LP to give us the outputs T prime and TR with the right variables in scope. If I had more time, this is where I would pause so that you can all go, ah, but I don't. And then there's this administrative thing where we need to convert between a lambda function as a Rock term and a lambda function as a LP function, but that's variable. And the last part that I prepared is that this translation is usually given for terms in CIC or CC omega, but we need to scale this to be able to use it as a practical tool in ROC. And this brings a couple complications. I will talk about two of those. One is that ROC's unfolding of fix is conservative, so some of the definitional equalities that the paper translations usually assume do not hold in ROC, because the scrutiny of the fix needs to be constructor-headed. So we fix that by just inserting some trivial matches so that the argument is constructor-headed. And the other part is handling records, which in the literature, usually those are represented by an inductive with one constructor. But that doesn't really work if we want the translation to be a record again, because if we start with this record, translate it to an inductive, what we get by the parameterized translation is an index inductive. But we don't have indexed records. Like, what does that even mean? We really want the translation to be a record which has these two instances of the original record as parameters, and then uses projections in the fields instead of building up an instance of the record in the index of the output. So it's pretty straightforward to adapt to this, but it's something that one needs to be aware of. And the other thing is that the records and inductives are not necessarily exactly dual, because for inductives we have this universal eliminator in the core syntax. That's the match statement, and we know how to translate a match statement pretty continuously. But records do not have this analog of like a universal constructor. So what we need to do is show you some scary types. We observe that relating projections by projections is okay, and you just need to trust me that this justifies that this relation is okay, because all of these things have the right types. But if we try to do the same thing for the constructor, that's not okay, because here we're assuming that the constructor should have all of the arguments of the fields unwrapped, while actually the real constructor that we are trying to use here has the arguments bundled as instances of the original record. And inductives so we need to generate some shims that we need to insert here instead of the actual constructor. We need to just wrap the constructor and rearrange the arguments a little bit. The same thing would need to be done for inductives if the primitives were the inductive eliminators. Which brings me to the end, where I will say that most of what I talked about is already implemented in the standard distribution of RocqLP, so you can use it now, except for the records. We haven't upstreamed those yet, but those are coming whenever I get to it. And this implementation is already used in POPL', and Troc is a bit more complicated, so they hand-roll their own implementation, but it uses all of those same ideas. I think it's fair to say that there is for now a caveat where RocqLP does not allow for representing mutual inductive types. Sometimes that bites you a little, but like you can get away with some workarounds. And I would encourage all of you to give RocqLP a shot. It makes programming fun again. Thank you.
So earlier you said that we do not have indexed records. Unfortunately, ROC's kernel accepts indexed records, but we still do not know what they mean.
Yeah. Yeah, I was wondering whether I should mention this, but.
So actually it's funnier than that. It's like the elaboration is preventing you from writing it, but if you directly metaprogram them, then you can make them accepted. Because the check was done at elaboration and not in the kernel. And
so where's the limit for the mutual inductive types? Is it because you can't program them, or is it because the user interface to receive the mutual inductive types is not there?
The higher order abstract syntax doesn't have a representation for them.
It's a minor point, but at some times there were a problem with the guard condition also with the parametricity translation. Because subterms sometimes get expanded, so like a constructor, when it becomes dependent, instead of being a variable, becomes a successor of something. And this breaks the guard condition, so this happens for some example, for instance, in the standard library. So do you have some, does it work, what you did for that, like for this example? So I believe, 1 year ago, there were a problem still.
I'm not sure. I didn't focus on this thing explicitly. I'm aware that there was an issue on GitHub for something to that extent, but as far as I know, this was kind of like before I started working on this implementation, so better ask Cyril.
The example is you take GCD typically. You try to do parametricity for GCD, does it work or not?
I haven't tried. But it's a good test case, thank you.
Next, thanks, Stefan, for
thank you
again. And I let you. So Matthew will talk about universes.
All right. Enhancing RocqP's universe level polymorphism in RocqP algebraic universes, consistency checking, and variance inference, if I can, in 15 minutes. Last time I did 1 hour and a half. So, universe levels in RocqP, typing and elaboration. You know everything about universes. If you don't have them, your theory is inconsistent. You get Girard's paradox, Herkens, whatever. You have a well-founded hierarchy indexed by natural numbers. Dependent products take the max, and usually you have a bottom universe, which we will call U0. It's predicative set in RocqP. The algebra of universes, you have variables, a bottom, successor universe, and the supremum, which is written like this in Agda parlance. We tend to write it like this in the syntax of RocqP. The theory is that 0 is neutral for max, successor distributes on max, max is idempotent, associative, commutative, and subsumptive, meaning that if you take the max of u and u plus 1, you get u plus 1. And universe polymorphism is pre-next universal quantification on universe variables. Pretty straightforward. Now, you have, of course, unification in the proof assistant. What happens? Well, Thiago found out in his PhD that the theory for this equational theory of universes is not unitary. You don't have MGUs in that theory. And the example is quite simple. You take 3 meta-variables, and you have this constraint. X plus 1 is the max of y and z. And there are incomparable solutions. None is the most general for this. What it means in practice is that in Agda Orlin, you will get stuck constraints requiring user annotations. We don't like annotations that much for universes in RocqP, especially because we also have a richer system with a cumulative hierarchy of universes where UI is included in UI plus 1, and it goes on the right of dependent products. So with polymorphism and constraints, you get bounded quantification on universe variables, which was introduced by Harper and Pollack quite some time ago, and that we refreshed for RocqP in the 2010s with Nicolas. What it means is that you can quantify on universes plus constraints, and the body of your definition should check according to this, under the assumptions of these constraints. So a priori, the consistency check you must do for universe polymorphic definitions is of this kind. You get a bunch of less than or equal constraints on universes, and you must check if some constraint is satisfiable under this, or implied by this. And then you can encode, as usual, equality by the conjunction of inequality in the two directions. Except it's not really like this that it was implemented, because it was really hard to handle the constraints of this form. So Hugo carefully looked at the way we can do type inference in CIC and found out that we actually only need to handle the green kind of constraints here. So constraints where you get arbitrary universe expressions on the left of the less than or equal sign, but only levels or the 0 level on the right. And you can actually enforce this invariant in type inference. And this actually means that no algebraic universe, so things that are not in the subset of just variables and 0, can appear in the term. What happens? Well, you have some limitations, and when you are trying to do some elaborations, you will need to be careful. For example, if I elaborate the identity function, I'm not giving the first argument, which is the type of the object I'm taking the identity of. I put type 0 there, so my meta variable x has type at ID of .u0, which is a global universe for the identity function universe. You type check, and then you find that you have a cumulativity constraint that instance of x must be greater or equal than type 1. Well, you can't instantiate x with type 1 because this is an algebraic expression. It's not type 0 or type L for a level. So what you do is that you just leave the constraint and leave this universe variable. And this is OK, because you only have constraints in the subsets that we were mentioning. So the pro of this solution is that you have efficient satisfiability and validity checking. This was improved even by Jacques-Henri Jourdan, who implemented a state-of-the-art algorithm from Bender and Targin in about 10, 15 years ago already. And at the time, we saw a 30% time improvement in checking. The cons is that you have this restricted algebra. The API is very error-prone. You must remember to refresh the things that you get from typing to not put them in terms if they contain algebraic things. This results in a proliferation of fresh levels and constraints, especially to avoid this forbidden constraints. What happens if you add polymorphism? Just the same. This adds a constraint that instances of universe polymorphic definitions must also only contain things that are non-algebraic. So you get the same kind of stuff, even with more fresh levels and more proliferation of constraints. Let's solve that problem using, as frequent in the type theory literature, an idea from Thierry that he worked on with Marc Bézem. So they proposed a new algorithm to solve the loop checking and uniform word problem for joint semi-lattices with an inflationary endomorphism. And what it means is that satisfiability is decidable for this max, plus, and less than or equal algebra in any semi-lattice, actually. It's actually a well-known problem. If you restrict the problem to increments in Z and solutions in Z as well, it's called the Max-Breton problem, which lives in NP intersection co-NP, which is an interesting class, for which usually we have polynomial solutions, strongly polynomial solutions, but in this case, we don't know if there is one. Weakly polynomial means it's the solutions are, the complexity is proportional to the magnitude of the increment. So if you have a problem with very large integers, you will get slow, but if you have just +1s and +2s, like we do for universe checking, it's not going to matter much. How does it work? We have basically a kind of logic programming forward search on a set of round clauses. So we are translating this constraint into clauses of this form. So you have a single universe here, maybe with an increment, but not a max. And on the left, you can have max. So exactly the kind of hard constraint with max on the left, max on the right, sorry, like this one. So here I'm building a very simple graph. And the idea is that we maintain some kind of minimal model of these clauses in the integers plus infinity, where infinity will represent a looping universe, basically. So the lowest universe will have highest value. So you see here S is the smallest universe, and it gets value 2. And W is at level 1. It's just one level higher, and so on and so forth. OK. I'm not going to go into the details of this algorithm. I'm just going to tell you that I proved it correct in ROC. I had to extract the proof from Thierry's and Marc's paper.
because they had a constructive proof on paper. It was constructive, indeed, yes, but it was really not even an algorithm. So we have an incremental version of this algorithm. So as soon as we find a loop, we don't care about the rest of the valuation. We just report a loop. We support an injective morphism, where there's just an inflationary morphism, so not assuming injectivity. And it's implemented as two quite complicated, nested, well-founded recursive definitions. It's sound and complete for the initial Solmi lattice, so Z infinity max and less than or equal. And if you use the fact that Z has a total order, it's also sound and complete for satisfiability and validity in this algebra. So you can think of your universes as before in Z or in NAT. I mean, all our universes are greater than 0, so it's easy to say, to see it as an algorithm for natural numbers as well. Okay. So it provides a pretty simple model for working with universes. You have an interface where just you're manipulating just a universe model, which always has 0 declared. It contains only this universe. Then you have a function to push some set of universes and constraints. And it's going to tell you, oh, there is a loop, or I can find a model. And then you have a way to check if some constraints are implied by some universe model. And it's reflective, so it can actually run in Roc, and we use that in MetaRoc. Okay. So now for the implementation in Roc itself, in OCaml, it's pretty direct translation. It's a functional program. We have some optimizations that are inspired by the previous algorithm to have a more efficient representation of the equivalence class of your universe levels. So a kind of union-find structure. It greatly improves the API of Roc. I can remove the refresh universes function. It's great. I love it. Universes can appear anywhere, so it's closer to Agda and Lean also. And we have a general substitution operation on these models that allow us to do instantiation of universes during elaboration, which is also useful. So still there is a problem with universe polymorphism and cumulativity, is that when we do elaboration, we have a large number of unnecessary constraints in universes that are generated. If I'm going back to the identity, I apply it to type at 0 and NAT. Then I get a constraint that I must be greater than 1 rather than an equality between them, which you would get in a non-cumulative system. But at the same time, without loss of generality, we could assign 1 to I without losing anything. The principal type of the expression will be the same, and even the conversion behavior of the expression will be the same, because however you instantiate this universe variable, the normal form of the identity goes down to NAT. So we're going to record how and where universes appear to perform this kind of simplifications when they're really not losing any generality. So the idea is to maintain some information about the variance of universes, how they appear in terms. You can have irrelevant, covariant, contravariant, or invariant. And actually, that's an idea that was already present in our work on cumulative inductive types with Timani, where here for the equality type, we can say that I, the universe binder, is irrelevant, as soon as EQ is applied to at least one parameter. The analysis is a bit more complicated than that, but I cannot go through it. But basically, the idea is that we can have soundly the rule that EQ at I of NAT and 0 and 1 is always equivalent to EQ at J of 0 and 1, living in the maximum of these two levels. And it's also the kind of the idea behind the template polymorphic universes. And the idea here will be to just leave this analysis to all definitions. For example, if you take the definition of relation, takes a universe and a type in this universe, you can look at the way it can be unfolded. You'll find out that this universe is also irrelevant as soon as relation is applied to at least A. So this enables us to do a sound first-order unification rule, and a faster one, because we don't need to compare irrelevant universes. And it enables also minimization of these universes. And this is compositional, so from relation you can look at proper, respectful, all the definitions of set-to-heteroid writing. Basically, you only have irrelevant universe. Same for containers, as you would expect. Things that use their types in a parametric way, the universe is attached to their type is going to be used irrelevantly most of the time. Finally, we have two modes to work with these universes when we are writing lemmas or definitions. You can do a kind of mixed inference mode where you bind the universes that you want to quantify on explicitly in your definition, and then the minimization will solve for these universes. So it will try as much as it can without losing generality to find a solution in terms of I and j, and it will tell you otherwise that some universes cannot be simplified. Or you can be in full checking mode where you control exactly what constraints and universes are allowed. That's it for me, I think.
One quick question for Mathieu. And could the next speaker come forward?
Cool. I was wondering, how does the whole model theoretic algorithm work with unification? Is it an easy extension? Do you have to do something complicated there to handle universe-level meta variables?
No, they're just treated like variables. Because you can express equality and less than on variables, and you don't need more than.
Okay.
It's important to have the instantiation function so that you can instantiate the meta variable, but otherwise it's simple.
You said something that worried me. You said, as soon as we have a loop, we don't care.
We report the loop. I said, we report the loop. And we don't care about the valuation of the other levels. Yeah. Because we can tell the user there's a universe for which you have I plus 1 is greater than I is greater than I plus 1.
So you can have very good information about where the problem is.
Yes, it's not producing minimal loops by default, but you can find them if needed. Yeah.
I think we need to move forward, but let's thank Mathieu again. And now we'll talk about the generation of induction principles. I think the users of ROQ will be very happy with this development.
Can you see at the back? Oh, it's the size. I thought it was the quarters. I can switch to light mode quickly. Color team. Is it better? To what? What is that? No, but so seriously, or do I do that?
Just take Control-Shift-P and then type in Zen mode. Go to the click on the top center. Control-Shift-P? Yeah.
Control-Shift-P? Oh. Ah, okay. Well, I don't know how much we'll see because I used 80 character per line. So, well, basically, it's a work that we've been doing with like Yannick, Mathieu, and Nicolas to finally have good eliminators for nested types, because so far in ROQ, they were basically more or less pointless. So, quick recall about inductive types. You define your inductive types in ROQ or lean, like list. All is reasonable. To be accepted, it needs to satisfy a positivity criterion, so that the logical consistency of the system is preserved. And then basically for every inductive type that is positive and is accepted, automatically an eliminator is going to be generated. So for the list, you just get the usual one saying if the predicate is true for the empty list, and for every element, every smaller list is true, then it's true for P of A.L. You actually get one eliminator per sort. So here we have the one for prop, we can get the one for S-prop, and so on. And so in ROC, these elimination principles are generated automatically as combination of fix and match, because those are the primitive constructors in ROC, and in Lean it's the eliminators that are primitive, and so it's the opposite. It's a function in fix and match that are going to be elaborated to eliminators. So what are nested inductive types? You may very well have seen the most common example of n-ary branching trees, also known as Ross tree. It's just basically saying a tree is made of a list of subtrees and so on, so it's n-ary. And it's so-called nested because basically Ross tree that you're defining appear nested inside another inductive type, which is list. And so these kind of inductive types are very useful because basically they enable users to have a more sophisticated form of recursion. You have lists, so you can have n-ary operators like match or switches. You can nest with option to be able to have an optional recursive argument and so on. And for these reasons, it's used in all the major computer science projects like MetaRock, VST, Iris, and so on. It's mentioned in the stuff that Lean needs to fix to finally be a good setup for computer scientists. Because the reason is that it enables to reuse libraries. For instance, if you have a basic function map on list and you want to define a function on Ross tree, you're just going to say, okay, I have a list of Ross tree. I apply my Ross tree map function recursively with the function map for list. And this way you define one library for list, for the containers you're nesting with, and you can just reuse them. So Ross tree is very simple, but you can actually really quickly get into very complicated nesting. For instance, if you just define like a notion of term, like some syntax, with an n-ary operator, like a switch, like a generalized if. Then if you want to define what's the typing derivation, you're gonna want to say, oh, all the branches of my switch have the same type. How do you actually do that if term is already nested? Well, you're gonna define an inductive predicate, all, which is basically the empty list satisfy the predicate, and if all my element pointwise recursively satisfy the predicate, then my list satisfies it. And then if you start defining typing derivation, you're going to say, oh, all my branches have the same type, which is return type. And so here typing is actually getting nested with the all predicate, which is a predicate on list. And so the lesson is basically that if your object you're manipulating is nested, so is going to be your specification. And this quickly gets very complicated in real-life examples. For instance, in MetaRock, the definition of typing is about 100 line. It's nested 15 times in 15 different ways, with sometimes several depths of nesting and several nested inductive type nested. It's kind of a mess. And you just need good support for that if you want to do this kind of stuff. So they're really useful, and yet justification for it is very folklorish. For positivity, it's just say, oh, they are mutual inductive types. And that's the folklore. For eliminators, they say, oh, it's some form of parametricity. I'm sure Wojtek can tell you about it. And so scaling that to dependent types is actually a real issue. So I don't have too much time to review that, but neither support for ROC or Lean is actually very good. What they do in both cases, they say, oh, nested inductive types are mutual inductive types. So we're just gonna, to see if we accept nested inductive types, we compute the mutual encoding, and we see if it's positive or not. Turns out neither ROC nor Lean actually accept the same stuff. Lean is too restrictive and reject the typing example I've just shown, even though it's very basic. And ROC is quite amazing because it manages to be both time too restrictive and too lax. So it's too restrictive. For some reason, you can only nest with non-mutual inductive type. Why? We don't know. And it's too lax because there's a bug, and you can somehow make some very particular inductive types accepted. Because basically they forgot to check, and that happens. They wanted to be smart and they got dumb. And so in each case, you still have this weird dynamic check, and it does weird stuff because it's dynamic. And so what happens is that if you define this type depends on B, just takes a Boolean and a type A. And you're like, wow, I would like to nest on A. But basically you say if B, then A, else A to bool. And so basically if A is going to be true, this reduces to A, and A is positive. But if B is false, then it reduces to A to bool, and then A appears on the left of an arrow, so it's not positive and you can't nest on it. And so basically, this type is going to be rejected, but this type is going to be accepted. Because it's going to compute a mutual encoding, start doing reduction, see that, oh, you have if true, so it actually reduces to A, and that is accepted. That is not really modular. That is really not great. If you had some crazy positivity annotation, maybe you could say, oh, it is positive only if B is true or something. But in real life, it's really complicated, and we don't know to do that nicely. And then for eliminators, it's a mess. Lin basically just gives you the eliminator of the mutual encoding and beautifies it. There's no reason for it. It just beautifies stuff on the fly with no justification. It does not compute as you would want, so they just add reduction rules. And why they do that? They do that because eliminators are primitive in their system. So they just can't afford to give you an eliminator that is trivial. Unfortunately, it does not work really well because the encoding clearly leaks. It blows up in size, despite the restriction that prevents typing from being accepted. And the R part, which is actually instantiating this eliminator, you still have to do it. And Rock, well, they just decided that if we don't know what to do, we do nothing. So if you look at the eliminator for ROS3, it's just going to say, oh, I have a list of ROS3. I don't know what's the induction hypothesis supposed to be, so I'm just going to do nothing. So it's not so bad because you can always write it yourself with fix and match because there's some support in the GARP for it. Don't ask me how, I don't know. But basically, you're just going to say, oh, if I have a predicate which is always true, then the parametricity is true. The whole predicate is true. Makes sense. If the predicate is always true, it's true pointwise, so it's true. And then you just define your induction principle by saying, oh, if I have a list and my predicate I'm trying to prove is true for all the elements of my list, then I can prove P of node. And then you just prove it by fixed point. Let's just say it's very, very tedious. So for typing of MetaRock, that's 100 lines of code, and the proof is 350 lines of code. So basically, you have to write 400 lines of boilerplate, 500 lines of boilerplate for a 100-line definition. That is awful, and I think we could remove several thousand lines in MetaRock if we could get rid of that and generate them automatically. There have been some work by Enrico Tassi using parametricity, as the folklore says, but sadly it does not work really well with type dependencies. So now let's get to our work. So basically what we did is that we've identified a subset of well-behaved nested types that can be determined syntactically to be positive. You don't need to compute the encoding. And syntactically, you can ensure that there is an encoding. And this subset basically covers all the basic examples, like ROS3, like typing. It's modular, and it has the very nice thing to rule out these ill-behaved types that really rely on the dynamic behavior. And once you've done that, basically, you end up with a class of inductive that you can always generate a whole predicate for, and that you can always generate an eliminator for. And so we've implemented this in Rock. It's been merged last night, so it will be part of Rock 9.2. So if you look at the list, now there's a common scheme all that is going to generate this list all predicate we've seen. So it's a bit messy, it's sort polymorphic and so on, because we have different sorts in Rock. So we need to be able to instantiate it with prop, with type, and so on. But it's just the usual thing that we've seen before. I have a predicate P of A, and I say, oh, for every element of type A, I have a proof of it. I'm just enforcing pointwise that my predicate holds. Then you have the theorem we've seen before that just says, oh, if the predicate always holds, then this always holds. And then if you define ROS3, you're now going to be able to get the good eliminator. You're going to say for all lists, such that P is true for every element of the list, then I can conclude that my property hold on the node, then I can conclude that it's always true for all the rows tree. And this list all for all is just going to be here to inhabit the fixed point. And it's really modular. If you start doing weird nesting like this, like here you nest with list, but functions of Boolean into list, so you have double nesting plus function, you're just going to get the good eliminator again. Well, it's a bit ugly, but when you do working with MetaRock, it gets ugly, you know. And so basically, the key thing is like this new positivity condition enables you to tell what is important, what is recursive or not. So for vectors, for instance, scheme all is just going to be doing stuff for the type A. It's not going to do... I forgot a variable, no? Ah, no, right. I have to do a print. Yeah, so basically you're just going to say, oh, for all my element A, P of A must hold, but for my natural numbers n that do not participate to the specification and to the type you're nesting on, you do nothing. And that's the opposite of parametricity. And by being smart like that, you end up managing to get out of the type dependency hell. So then you can just have like a vectree, which is like every tree must have a fixed size. You can also nest with prod. Something nice is that now there's a new setting to make the generation automatic. So if you just write set def scheme all, it's going to generate this all predicate twice. It's going to generate prod all, and it's also going to generate prod all, which is the prod all predicate for prod all, which can be useful when you start having a bunch of layers of nesting. This is going to work great. And finally, something that happens very often is that you nest only on one of the parameters. Here for product, you nest on A, but not on B. What happens is that it's just going to inline a predicate fun true for the predicate that you need to give, but that you have not nested on. But there is also a scheme command to generate all predicate only for some parameters. So here, for instance, we can say, oh, I want an all predicate, but only for the parameter A. And in this case, you're just going to end up having like, oh, I have my type A, a predicate on it. I have my type B. I don't want to nest on it, so I'm not generating a predicate for it. And I just get the prod all without the predicate on B. And so once it's registered, if we look at the induction principle, if we regenerate it, we are now going to have prod all 10 of left tree. 10 is for 1, 0. It's like A but not B. And you won't get this fun true that is was basically around before. And so it's quite nice for a few inductive types that you only nest on some parameters, even though a bunch of them could be nested.
So how do you tell that you want to use this new asymmetric protocol version?
Well, for instance, in MetaRock, they have a... Oh, it's quite simple. It looks at all the arguments. Yeah, it looks at all the arguments, check which one are nested, look if the specific one has been registered, and if not, it just falls back on the general one. And if it's not found, it just creates a warning saying your eliminator is pointless. Voila, and then it works on typing. You're just going to generate the all scheme for list all, and then you get at the twice level because you have your typing derivation, which is nested with something that is nested. And then if you generate the inductive predicate, you're then going to end up having list all of all that appears. And it scales really well, so we're quite happy. For the moment, this default is set to 0 for two reasons. First, there's a few repository in the CI that needs to be fixed. For instance, MetaRock has a problem with sort polymorphic definitions. And hopefully in ROC 10 or 9.3, this will be set to 1, and then we're going to get nice eliminators by default. Voilà.
I'm not convinced.
I'm not surprised.
You choose the all approach, but why would the all approach be the one that your user wants to have?
Well, basically, we've still shown in the paper that like this eliminator can prove the eliminator of the mutual encoding and the opposite. So basically, we know that this eliminator is a valid one. There might be different formulation of it. You may want to define this list all as a fixed point, but basically it's a register scheme comment, so you can always choose not to register it, not to generate it, and register a custom one. It just needs to have the expected type.
But I had the impression that you might want that when processing the list, you might want to inherit something from the first elements in the processing of the flowing ones, like in fold or something like that. So in that case, it looks like your OR approach is going to miss some computation power.
So what you say is true is that there's always a more specific inductive principle that we can have, but the same way as the inductive principle with list is supposed to be universal and enable you to prove everything, including the more specific one that you would want for your problem, this one should be able to do that.
Yeah, well, there's an obvious one, which you would have for lists or vectors, which is by index.
Sorry?
For all n list of n and p of list of nth list of n. Sorry, you have the all expressed within an indexing with a for all n p holds for the nth element of the list.
Actually, it's much more complicated.
Oh no, it's for many applications this is what you want.
Yeah, maybe.
Because you're indexing, you're thinking of that list of thing being a vector, and you want to index with it. So whenever I have to define these predicates, this is usually the form I use.
Yeah, but basically what you would have to do that is to like specify, if I understand correctly, you would have to define what it means to be in a list or stuff like that. No? You say for all element in the list with an in predicate?
Oh, for all index n, the nth p holds for the nth element of the list.
Yeah, but then you have to define nth and so on. It's not so easy to define.
But you have nth.
Yeah, you have nth, but like how do you define nth for typing? It's just that like list is so specific, there's a bunch of ways to reason about it, but if you really want to be systematic, I don't see any other way, and we've proven that it works. So it's systematic, not necessarily the best option for what you want to do.
Last one.
Is the list... the list all, I didn't quite understand why you needed double. Why can't you use list all of list all?
List all of list all?
Yeah, like nesting, because list all takes a thing on like data prop and then produces a list data prop.
Maybe you want me to show you what
list all of the thing, wouldn't that give you what list all does?
List all, so list all, it's the all predicate for the inductive type list all. And basically it's saying, oh, if I have A and a predicate, which is going to be typing, and a predicate on typing, then I can prove that my list all is holding. And the thing is that when you're working with MetaRock, in most cases, you're actually going to be non-dependent for your specification. In this case, this list all can basically be brought down to list all up to one issue, which is basically that like the common definition of list is not sub-polymorphic. So if I'm non-dependent, I still can end up in prop or S-prop or something. So I can't just instantiate list with S-prop since it's going to type. And so this issue is basically why we have to generate it automatically. But there really are better instantiation depending on what you're doing.
Usability question. So assume in my library I already have a definition of list all that I handwrote in prop, but I don't have one in type. Is it possible to your setup to register my custom definition for prop while still using your auto-generated definition for type?
No, it's not supported.
Okay.
It actually didn't really arise because no, it didn't actually arise because yeah, I guess we could do that.
Okay, I think we need to stop now, but thanks again. So, It's actually the last talk of the session, so you will have a break eventually in time. So the mic is just...
Mine is moved to the next session? Are we having the break
No,
right now?
No, it's your talk now. So tomorrow we talk about RocQ and parametricity.
All right, so I'm presenting about RocQ parametricity translations today for inductive types. I don't have much time, so I'm gonna start with the motivation, then bring a bit of the context of the RocQ proof transfer framework, and end up with a few examples of a derivation for this parametricity translation that I'm generating automatically. So let's start with this definition of types. On the left-hand side, you can see a unary representation for natural numbers and a binary representation. And on the right-hand side, you can see the definition for integers. And it might have happened to you that you have proven a more general lemma, a lemma for the more general type, in this case Z, and this appears to you in the form of NAT, for instance, in the commutativity of addition, or that you know how what the result is for folding the addition over a list of natural numbers, and you want it for the folding of the addition in Z, or you just want to have again the good reasoning principle that you have on natural numbers, but on the binary representation. So one would like this to be discharged just by pressing a button, and my colleague Vojta here presented that, you can do this using parametricity, and it has been done previously. On the dependent type setting, it started with the raw parametricity translation, which then was enhanced by the remark that this translation preserves type equivalences in the univalent parametricity translation. And in parallel, there was RocqPL to change representation between refined data types. So the latest framework to do proof transfer using parametricity is RocQ, and it generalizes over these previous parametricity translations. So on the left-hand side, you have a few examples of what you would like to transfer from one type to the other. So for transferring the 5 natural number into the 5 in Z, user has to provide a relation, the embedding relation from NAT to Z, and RocQ would translate type NAT into type Z. And if you want to translate from list of NAT into list of Z, the user has to provide a proof that this type parametric container list preserve the embedding relation. And if you would like to transfer the contained type in vectors, you will, without translating the indices into another type, you will need to provide a relation from NAT to NAT. So I'm presenting an automatic derivation for generating what the user has to provide for 2 and 3 automatically for a restricted class of inductive types, which is with type parameters possibly performing recursion, but no indices for the moment. This is done automatically. So now a bit of context. Roc is able to support weaker relations by using asymmetrical presentation for type equivalence, in which you have this sigma asking for a relation, and you describe how your the maps that go from A to B, and how this, and on the opposite relation you have another map, and this describes a hierarchy, and the closer the map is to type 4. In this case, I'm going to show what maps looks like. The closer is the relation of being a type equivalence. So we start at the bottom with M0. This is a map that only requests a relation between the two types. Then you have to the user would have to provide a map from A to B. Also providing what's below, and the level above splits into two different ways. So on the left-hand side, you need to provide a proof that the graph of the map is included in the relation, and on the right-hand side, that the relation is included in the graph of the map that you are giving. So above that, you have both of these intermediate conditions on the second level, and at the top you have a coherence proof saying that the left-hand side, when composed to the right-hand side, cancels out. So there's pros and cons from the from the side of the user when supporting weaker relations. The pros being that you actually can proof transfer using weaker relations, and this enables avoiding the use of the univalence axiom when possible. And one of the cons is that, they're currently, so previous to this work, there was no automatic generation, so the user would have to prove for every level of the lattice that the type parametric container preserves those types of relations. And if you don't want to translate a term, you would have also to provide that your type is related to itself at every possible level in the lattice. So now this is the part where I show how these terms look like, and I'm generating this automatically, but I'm just showing an example here. So the strategy I take is to build bottom-up, to make a bottom-up derivation of this lattice, so as to avoid the use of the univalence axiom when I can afford to do that. And this requires a careful implementation of this intermediate level that's so that when you reach the top of the lattice, you can actually prove that the composition of these two intermediate data can cancel out. And the strategy is by postponing the elimination of identities. So this is, I gave LP a shot. I'm building upon the binary parametricity translation plugin that's available in LP and on top of Derive plugins. And I'm automatically generating this, that the type parametric containers preserve relations across the containers, and that the types relate to themselves at every level. So far, for levels n,0 for every n that you can have in the lattice. And you can find it on my personal fork of the truck repo, and hopefully one day will be merged in the original one. So now an example derivation. This is the parametricity translation for the natural numbers. It relates 0 to 0, and for every related natural numbers, the successor of those numbers are related. The map that you give, it's the one that maps every constructor to the same constructor and spreads to the subargument the application of the same map. You have to generate projections for every argument of every constructor, and to show at some point that this composition cancels out, but not in this case. You can see how this could be difficult, and it's not. This is not something that you would like to do by yourself, and this is why we're trying to do it automatically. And the strategy about avoiding the elimination of equalities is done in this way. So for generating the left-hand side, I do induction on both cases of the inductive type, and since I have an hypothesis, it's meaningful on the diagonal because you can discriminate outside it. On the right-hand side, you do induction on the binary parametricity relation, which also instantiates the inductive types on the diagonal, which then in the coherence property get to compute if you do induction on the relation, and you get a term that gets generated in the middle that you can prove that you can cancel as well. And you can do this regularly for the inductive type class that I described. And just to give you a hint of how this looks like for Lisp, I'm avoiding the boilerplate. This is just the terms that you have. This is just the type of the terms that you need to give to truck, and I'm able to generate that terms with those types automatically as well. So that's all I have. I'd be happy to take questions.
Questions?
There's something I did not understand in the talk, because you showed, in the beginning, you showed two types that are the same semantics. But then when you talked about NR and list R, you were relating two types that were the same. So where's the gain?
So exactly. So this. So there's no automatic way of generating the relation between two types like arbitrarily, but because how it's done in proc, the user currently has to give these relations for relating the type to itself, for being able not to translate the goal from, so for instance, if you have a type that you don't want to touch in a goal, appearing in a goal, you need to provide this kind of relations. And this is, for the case of NAT, of course, relates the type with itself, but for the case of lists, it's relating, so given that you have a relation on the type parameter, you have related lists on the related, yeah.
Hey, so I'm just curious, like, is it a time issue or is it an issue with indices? Because you say you don't cover it yet.
So yeah, I haven't addressed it yet.
Other question? Okay, so let's find our speaker again. And there was supposed to be a last talk of the session by Basile about verifying synchronous data flow programs using SMTCOC. Unfortunately, he couldn't do it. Some financial issues. So if you're French, you know we don't have a budget, and so that's the problem. So that's the end of the session, and we reconvene at 4 p.m. So this is the break. So see
All right, let's get started. Welcome to the last session of RocqPL. So this will be our certified proofs and programs session. And to kick us off will be Jean, and he'll be talking about verifying the Vickrey-Clark-Groves mechanism. Thank you.
So, good afternoon, everyone. I'm here to present our project, which applies the RocqPL theorem prover in formalizing the mechanisms from the auction theory. And I am Zhan Jing from Shanghai Jiaotong University. I'm currently a master's student, and the project is collaborated with Professor Pierre Jouvelot from Mines Paris. The type of auctions that we study today is called the sponsor search auctions, which describes the scenario where multiple sellers compete with a process of auction in order to determine their position of attractivity on the web page when a relative keyword is entered by the web user. For example, in this picture, we illustrate an example of the Google search engine, and the keyword entered is about the cars, so that the sellers will show up as the slots, each linked to their information on the website. Different from the well-known auctions, where it is implemented in a public auction house, and the auctions bid in multiple turns. The cell-bid auctions is implemented through a private protocol, which means that the agents or the bidders cannot see the bidding values from the others, and which is different from the artwork. And the only one who can see all the bidding values is the auctioneer, and she's responsible for allocating the items to each bidder and then determining the corresponding price. So before detailing about the sponsored auctions, I would like to introduce a little about the motivation in studying the auction theory. The auction theory is a branch of the algorithmic game theory, and we start with a simple case where there is a single item, and a natural strategy for the auctioneer is called the first price mechanism, where the highest bidding agent gets the item and is asked to pay the price that she bids. However, this does not generate a stable strategy for the agent, because the winner would always like to underbid in order to get the item with more money. A better strategy is called the second price mechanism, where the agent can get the item with her highest bidding and is asked to pay the second highest price. In this case, a great property is guaranteed, where the truthful bidding, which means that to pay her highest affordable price, is the best strategy for each agent. Since if she underbids, she will always have to pay the second highest price. And instead, if she overbids, and by coincidence, there is another agent that has a price which is over her highest affordable bidding price, but is lower than her overbid price, then she has a risk of losing money. And the economic theorists find this property with the mechanism interesting and would like to extend it to the case with multiple items. However, it does not work by simply allocating a higher bidder to a better item and ask them to pay with the bidding price right after theirs, which is as known as general second price. This does not guarantee the good property. The case that it works is called the general VCG, Vickrey-Clark-Groves mechanism. And in this kind of mechanism, each agent is asked to determine a price over a combinatorial subset of the items. So that, of course, it is a general case of the sponsor search auctions. And in reality, there are platforms that runs on a version of the sponsor search auctions and is announced by the theorist to be a specific version of the general VCG applied in sponsor search. And however, it runs with a complete different algorithm with the general VCG, and this is where our interest lies, that is to verify this with the formalization tools. So we come back to the main notions in the sponsor search auctions, where there are multiple agents and who bid for the multiple positions. And for each auctioneer, she's responsible for allocating each agent to at most one slot. And in each as agents, there are always more agents than the number of slots. And for each agent, there are some notions related. She is asked to bid a fixed price, which reflects her expected payment for a click by the web user. And the valuation is a notation for her highest affordable payment per click. And the real payment is determined by the auctioneer. And for each winner, her utility is determined by the difference between her valuation and the payment. And if she loses, her utility is 0. And for each slot, there is a percentage related, which reflects the attractivity percentage of the slots compared to the other slots. So it is better to describe with a picture, with an example. So there are 5 agents, and which bids from higher to a lower price, and is allocated to the better, to the worse, or to the worse slots. From here, we already have seen the problem of the nuanced problems, which is there might exist people with equal biddings, but they can be allocated to the distinct slots, and there may exist slots with the same attractivity, but they are allocated with the different bidders. And we ask in the current version that if this property in the sponsor search auction is so guaranteed, and the final payment from each bidder is determined by the user. That means if the web user clicks on the click-through rate, then the bidder have to pay for it. So the VCG mechanism for sponsor search guarantees 2 important properties. The first is it maximizes the social welfare, which is a function that sum over the bids that wins in the auction. So by intuition, we know that this can be realized with a sorting algorithm. And the second one is the interesting one, we have talked about it, is that bidding once valuation is the best strategy for each agent. And on this situation, we call that it is a truthful agent. And in reality, the VCG version for sponsor search is implemented through a sorting algorithm. And the general VCG is implemented with searching for arguments that maximize the social welfare function. They are implemented completely differently, and we want to formalize that they are equivalent. So the concerns is theoretically VCG SS is a direct application of general VCG, and algorithmically the cases with equal bidding case might influence this kind of equivalence. We implement with RocQ. The first is we parameterize over the tie-breaking functions in general VCG, so that in each kind of tie-breaking way, which means to choose each kind of combination as the outcome, the property of the general VCG is always guaranteed. And for each agent, her utility is guaranteed under each equal bidding cases. And the proof approach we use is functional, which means that we abstract the general VCG as a function with the parameters, including the tie-breaking ways, including the social welfare functions, and we pass the structures of VCG as the values into the mathematical terms of the general VCG in order to get the equivalence. The repository on GitHub is called MicPonV. It is the certified library for auction mechanisms from 3 parts. Firstly, it determines the core definitions for auctions and specifically for sponsor search auctions, including whether each agent is a winner and the price utility related to hers. we have a dependency of the classes of distinct mechanisms. Relatively, the bubble sort is independent. That independent file that determines the bubble sort, which constructs a link between to maximize the social welfare function and the bubble sort. That each time with the sorting algorithm, we can get the the social welfare function larger. And the MEC point V is an abstract structure over all kinds of mechanisms, including not only auctions, but also matchings and voting mechanisms in game theory. And the VCG folder includes the files including the general VCG, the VCG versions for sponsor search, and how we structure them together. And in the current version, we move the hypothesis where the tuple of bits and the tuple of click-through rates must be unique, which is always eliminated or simplified as the true in the economic theory. And we formalize the properties, including that in each kind of combination, the general VCG is always truthful, and that's how we pass the values from the VCG as into the truthful VCG to get the equivalence between the price. So the things that we would like to talk about is firstly the necessity of introducing the argmaxes when we use the general VCG with multiple combinations, because when there are multiple combinations, the argmax is arbitrarily, and we would. So we stop here with the contributions, and I'm happy to wait for your questions.
Does anyone have any questions? Just raise your hand and we'll bring you a microphone.
So what are the background theories that you rely on?
The background theory about the formalization is the auction theory.
But in the formalization?
The ROC implementation with the proof approach that is functional.
Okay. I have a second question. Why is it important to work on bubble sort?
Since it is that in the general VCG, we would like to find the argument that maximize the target function, which is here the social welfare function. And in sponsor search, the larger bidder is allocated to the higher click-through rate, so it is implemented with a sorting algorithm. And the bubble sort algorithm is used to verify that when we swap each pair of bidders, the larger bidders allocated to the higher click-through rate can realize that the maximum social welfare function is reached.
So it's important because you have a specific look at pairs of bidders.
Yes.
You seem to have spent a lot of energy dealing with breaking ties.
Yes.
Is this correct? In other algorithmic endeavors, like when you work in geometry, when you have this kind of difficulty, people introduce infinitesimals, and then they break the ties because nothing is equal to things are no longer equal, right? Would that have been possible in your case?
We haven't thought about this kind of solution. And in our case, when there is equal biddings, so there are a set of arguments that maximize the case, and also in the sponsor search with the sorting type, there is multiples. So we can only guarantee that for each singleton that is chosen by the sorting algorithm, it corresponds to a solution in the general VCG, and the property is guaranteed.
Can the next speaker come up? While we're doing that, we have time for one more question. If not, let's thank our speaker again.
Yes, thank you.
Trains everywhere. Okay, our next speaker is going to be Harry from Swansea. He'll be talking about reasoning about trains.
The railway logic, we prove it to be correct using formal methods, and I take the result of that and prove it to be correct in ROCq. So to kind of give a bit of an overview of what I mean, so we take the interlocking, so the logic that controls the trains, and we do testing on it against some standards. And because we don't want the trains to crash, there's about 7,000 to 10,000 properties or so. So this takes quite a long time. And a way of getting around this is that we can encode our interlocking into some kind of format for verification, do the same with the safety conditions, and then in theory, once you run it through the verification tool, if this passes, it should go through testing fairly quickly. And bear in mind, testing takes, say, 6 weeks. This takes an hour or so. So you speed the process up. And if you have to make a mistake, so if you make a mistake and have to start again, in theory, you should get the error earlier. But the problem is, how do you actually have trust in what your verification tool is doing? Because they're very complicated and not many people actually understand the deep logic of it. We perform some proof checking, and the idea is, again, that you still have the encoding. You take the result of the verification tool, run it through another tool that checks its output, and then once those two say yes, you can perform the standard testing that is obviously needed to get the accreditations and all that. This could be done two ways. We could make a checker ourselves, but what we do is we use ROCq so that in turn we can prove that the checker that we are making is also correct, which adds another level of safety and sort of validation to the overall process. And why are we doing this? Well, you have SMT solvers. In our case, it is Z3 from Microsoft. They're often applied to these safety critical systems. However, there could be flaws in optimizations that are used to produce said results, and you don't know if they're incorrect because it's so complicated. I genuinely believe there's one guy in Microsoft who knows everything, judging by the GitHub repository. If something happens to him, I'm in big trouble. That's all I'm saying. And we want more than a true or false result. And if we do this proof checking, we get an actual certificate. And so my goal is to build a verified proof checker, which will independently verify Z3 rather than Z3 just saying, yep, it's great. And why this matters is it increases the confidence of using the verification tools in that overall tool chain I showed you just now. So, Z3, what does it do? Well, it produces some proofs. And when it produces a proof, it gets back a proof log. And it is made up of these 4 types for the SAT logic, so that's what we focused on to begin with. We have simply assumptions, which is what the initial interlocking logic was. We have RUP steps, which I'll go into in more detail in a second, but this is using resolution to derive new clauses from anything that was existing. Eventually, you'll get to a point where it derives a contradiction, the empty clause, and therefore you know it's a valid proof. You have Soyton steps, which simply perform the Soyton transformation to take something that is not in a CNF, conjunctive normal form, and make it into CNF, but critically, nothing changes in terms of the satisfiability. And then if ever we produce something that makes something redundant, we can delete it. So I said about RUP, well, this is the foundation of the whole proof format, so reverse unit propagation. We take a clause C, which is made up of some literals, and it's valid if you take every single one of those literals, negate them, add them back to the original formula, and by this unit clause propagation, it makes everything refutable. And for this, we've developed a proof structure to show this is correct. We called it a tree proof because it looked like a tree. I'm not very creative with names. And what this means is, say you had A that was derived by RUP, you could add the negation of it, the A, and this shows that via one cut and then another cut with another existing clause, you would get a contradiction, and therefore that A would be a valid step. With Soyton, well, it's slightly different to what usually happens. Z3 takes the fresh variables that are usually generated and puts the original formula back in, which is quite nice because it makes everything a tautology. And then what Z3 does is it uses these tautologies in RUP to cut down and learn some more steps. And what this does in our checker is we validate it by matching it against any of the known patterns, because there's about 8 patterns, and if it's not one of those, it simply can't exist. It also has some clause learning, where there's 2 components. There's the left-hand side, this antecedent, and the resulting clause on the right-hand side. The right-hand side is the bit that's used by Z3 for further steps, and if it knows something in there is already false, it just cuts it out to save RUP some time, but it's still based off the original tautology. In terms of proving everything to be correct, the first thing we did, as I said earlier, we have a checker that runs to check the unit clause propagation for RUP. I built the tree level structure, and then for every step of the way, we basically proved that we have a corresponding tree. So from the start, you'll have a proof of the start. Every time you do a cut, you'll have a proof of that cut. And at the end, you'll have one big tree that showed from the start, you could show an empty clause. And then we could feed this into the overall proof system. So this is all, as I say, all done in ROCq. And the basis of that is logical entailment, such that if you have a set of formulas and you have another clause which is part of it, if one is modeled, the other one has to be as well. So we want to show everything to be logically sound, and in our proofs we have these assumptions, which is what we start with. We have the conclusions, which is what is derived. Every step of the proof log adds another one of these conclusions, and we simply say that if the assumptions are modeled, the conclusions must be modeled. And every time we add something or remove it in the deletion case. And then the critical thing at the end is if the unit resolution derives the empty clause from the original set of assumptions, it therefore means that the assumptions have to model falsity, which obviously can't happen. So we have that the original formula is unsatisfiable and our proof is therefore valid. So in ROCq, what we did, we went through each step and we showed that this relation holds, such that if you add an assumption, well, if you discover an assumption in your proof log, well, because it's on both sides, it keeps the entailment. With RUP, because you're deriving something from something that was already existed, and if you have this relationship before, again, you're still going to have it. Soyton steps is a new technique where we replace the Boolean variables with the originals, which make the tautology, and if you're adding a tautology to something, you're still going to get your relation. And deletion is if you're removing something that's redundant because you've already got a sort of unsat core as such, you keep your relation, or the opposite of that. Some actual proofs, because I thought it'd be a good idea to show those. So with the theorem on the left is sort of the main thing we came up with, such that if the checker says yes, you preserve that A modeling C relationship with logical entailment. And then we made another set of proofs such that if the checker passes and it comes back with an empty clause, i.e. that the last step was indeed a proof that we've derived the unsatisfiability, the original set of assumptions are unsatisfiable. If you want to see all of this, you can. It's not that exciting. Okay, so then comes the exciting bit for what I thought was exciting and why I was really intrigued by Matthew's talk this morning, because we're trying to extract this so we have verified code, and currently we're going to a camel, and industry would love it to go to C++. So when that came up this morning, I was like, yes, this is great. So what we did is we evaluated the proof checker for applying results from 2 techniques that our partners use. One is inductive verification and bounded model checking is the other. Bounded model checking is far more complicated, hence why the number of lines for the proof logs are much larger, but that was basically to stress test this thing. In reality, inductive verification is what it'd be used for, and that takes about 30 seconds, which they were quite happy with. And what I should stress is that when I told this to my supervisors, they didn't believe me. The proofs are literally all the rewrite steps to get to one point where it goes RUP says, yep, you have a contradiction. Don't quite know why it does that. Who knows? Okay, to summarize, what we're doing is we have some independent verification for Z3, such that when we apply our verification tool to the railway, we can confirm that it's actually doing what it says it's going to do. And in terms of keeping the correctness, we're using ROCq, because otherwise, if I just wrote it myself, there's a very high chance that there would be some errors. This way, at least we have some formal correctness alongside it, which, as I say, adds another level of confidence to the verification process and hopefully does make the railways safer, which I'm sure everybody would quite like. So the next steps for me are to formalize and prove the further Z3 rules so that we can expand it to the SMT logic, and that will allow us to use this on all of our verification tools, not just the one that we've currently applied it to with the SAT logic. For this, we're trying to make a foundation that's sort of a plug and play kind of approach, so that as new rules are developed, it's as easy as possible, kind of how we did it with the whole logical entailment proofs. And the last stage is to basically perform as much industrial testing on the final checker. As much as proving it to be correct with ROCq is fantastic and brilliant, the industry and the engineers, they like testing. So if we can have the proofs and the testing, they'll be really happy. So, thank you.
Do we have any questions for Harry?
I was just wondering how it relates to the existing SMT COC works which verify certificates of SMT.
Yes, so we've looked into that. The sole reason for doing it externally was that Z3 introduced a new format, and the industry wanted something that was basically built from scratch that they could take away. And as I say, I'm going to do testing, but they want to basically line by line this, and they know what's been done effectively. We have looked into it, and it is a basis for some of the things we are doing. And if there's ways to cheat and not do it again, then I will use it.
So I've talked with people who do certification before, and they're often very hesitant to pick up formal proofs. Do you have ideas on how, like, are certification authorities or the people doing the testing interested in these level of proofs?
So the people who so the best way I can answer this question is they're not. But because in the sense that in the UK, when the industry tries to say they've got these proofs and they go to Network Rail, for example, and Network Rail go, well, it worked first time, that's impossible. But in the sense that that's why they want this tool, because it's a way of making something a proof without it being a proof, if that makes sense. Because it's something they can see running, they can understand line by line, and it's almost hidden the proof from them. That's the way we sort of described it.
So if I understand well, the specification of what you proved is, in fact, it's important. Myself, I would not really trust the fact that you just say it's been proved. What is important is what has been proved.
Okay.
So the specification is the basic rules of the SMT solver?
So what we're proving is the rules that the SMT solver uses in order to derive unsatisfiability. And when it does that, it prints back this big log, and it says that I've done this, I've done this, I've done this. And what we're checking is that for every single rule, if I applied what it has done, given that rule that it's told me it's done, is that possible?
Okay, thank you.
We have one last question. If the other speaker wants to come up.
Yes. There are several formats for exporting SAT proofs from SAT or SMT solvers. Can you, you said you wanted to use the recent Z3 format.
Yeah.
Can you very quickly summarize the main differences, for instance, with respect to the DRAT format, which is used by other solvers?
Yes. So, best way to describe it. In the short way of looking at it. Sorry, I'm used to explaining this in like massive answers. I can.
Maybe we can take this off.
Yeah,
that's probably the right way to do it. Okay, let's start there again. Are you mic'd up? Okay, very good. So our next talk is going to be from Jairo, who's going to be talking about doing some stuff with MathComp. Thanks.
Yeah. Hi, everyone. So this is some work in progress on formalizing what we call a first-order differentiable logic. So first of all, like an introduction to what quantitative logics are that we will use to define differentiable logics. And I'm going to do it through a little example. And the idea is very simple. Like quantitative logic is just a logic that models some subset of the extended real numbers. So basically you have a mapping that goes from formulas in the logic into some number in the real line. For example, in good old logic, you can interpret conjunction as a minimum. That's the basic idea of it. And then we say that a differentiable logic is thus a quantitative logic where the functions on the other side of the interpretation happen to be differentiable. These logics are useful for machine learning stuff. So just in case, like a little mouth opener about machine learning, the idea is that you have a loss function and you want to approximate the minimum or the maximum is equivalent of this thing. And this loss function includes as a parameter a neural network. And you have some data, inputs and outputs, that are assumed to come from an unknown function that here I represent with h, right? So you can think of this process, or as the neural network, as an universal approximator of some unknown function, which means it's not very trustworthy, right? Because it's an approximation process. We can try to make it more trustworthy through these differentiable logic stuff by imposing some extra constraints. So like the idea is that you are going to try to integrate symbolic knowledge into this fuzzy approximation process, and you can do that by modifying the loss function or modifying the architecture of the network through some formula in the differentiable logics. So you move into the real semantics, and because you're in the reals, you can integrate it into the optimization process. They also happen to be useful for giving programming support for this kind of process. For example, the vehicle language is useful for integrating this kind of symbolic knowledge into training. So you can write a specification in the logic, and vehicle is going to compile that into a loss function that you can use for training. So we would like to have guarantees about the performance and correctness of tools like vehicle. There is a problem, though. Like these logics, quantitative logics, can either come from the logic community or from the machine learning community. And the ones from the logic community are very nice from a proof theoretic perspective. So like they have these usual properties, completionality, residuation law that I'm going to talk about later, and have a calculus and all that stuff. But they are not very nice for optimization because they are not differentiable or discontinuous or all these different things. So for example, you have substructural fuzzy logics. But if you move into the machine learning community, you get these quote-unquote logics that are good for optimization, but are not really logics. They don't have a calculus, they don't have semantics, nothing like that. So it's just a mapping between formulas and functions that happen experimentally to work for this kind of thing. What we want to do is to build a logic that is both things, good for optimization and has good proof theoretic properties. And we call that logic soft bunch logic, and we say that it's a well-behaved differentiable logic. So the idea of the logic is that we are going to pick some semantics by this guy called Matteo Capucci, which introduces a softness modality that will be useful for this kind of balance. We pick bunches from the logic of bunch implications and hypersequence from fuzzy logics. I'm going to talk a little bit about this later on. And of course, we want to guarantee that what we are doing is correct using MathComp, and that means also extending the library a little bit. So here's like a minimal example of the logic. It's inspired by linear logic. So you have both additives and multiplicatives, with the difference that the additives are going to be, maybe it's too tiny to see, but a little p that is going to be a rational number. Semantically, then this thing is, I hope you can see, but it's basically a p norm. So you have everything to the power of p, and then you add it up and wrap it in 1 over p. And this is nice because as p grows bigger, it approximates the maximum, which is known to be a lattice operation, just like the additives in linear logic. So like the idea is that you're going to use this p parameter to balance like behavior of the additives and continuity, right? Because the maximum is not continuous. Then you extend everything into the extended real numbers because you are going to interpret top as infinity and 0 as bottom. And multiplicatives are given by division and blah, blah, blah. So to do this, we will need to modify the power function in matcomp because it proved insufficient. I will talk about that later as well. So here is the structure of bunches I have a sequence. Just in case you're not familiar with bunches, basically the idea is that just like you had multiplicatives and additives in formulas, you will do the same at the level of context. So the comma is going to represent the multiplicatives, and the semicolon parameterized by p is going to represent the additives. Hypersequences are basically list of sequences, and we are going to interpret this bar basically as a disjunction. Just like the white space in a calculus is sort of a conjunction of sequences, we are going to interpret the bar as a disjunction of sequences. I don't give the full semantics of sequences and hypersequences, but this is like a mouth opener. We're going to interpret everything on the left side of the sequence as a conjunction and everything on the right side as a disjunction, either additive or multiplicative. And we say that a formula is valid if it's bigger or equal to 1, basically. Which at the level of sequences means that the thing on the left is smaller than the thing on the right. So for example, we have this prelinearity formula that is known to be valid in the logic. Why we care about this? Because this is an important formula from the perspective of fuzzy logics. It's basically what makes something a fuzzy logic. And the problem is we can only prove this using hypersequences, and that's why we have them. We also have a calculus that is known to be sound, and we are currently working on extending that calculus to make it complete. Here's a little taste of the calculus. It's basically the calculus of bunch implications with these additional rules that are useful for moving around, playing around with the p. Basically, you can make the softness parameter bigger as you go up the proof. Ideally, we want to, when we are done with the propositional case, move into the first order case, which means we need semantics for quantifiers. And well, we had the semantics for disjunction where addition, like the p-mean, the p-norm for two elements. So we are going to generalize that into the infinite case, and the infinite case of an addition is sort of like an integral. So that's like the intuition as to why we picked this. But this is still just a p-norm. But here it will be specifically over a probability space because it gives us some extra properties that are nice for optimization and also to behave more like quantifiers. Similarly, this thing is also parameterized by a p. And as the disjunction case, as it grows bigger, it approximates the supremum. But also when it grows smaller, it approximates this thing, which is called a geometric mean. It's just like a characteristic of the logic. And we can define universal quantification as usual, as the dual. But for this, we will have to modify what validity means, right? Because now we have to deal with variables and all these things. An important lemma that will be useful for like extending validity is that these semantics for quantifiers are monotonic, right? Like if it's monotonic increasing. But to prove this, we need to use Hulder's inequality, which is this thing. And unfortunately, in MATCOM right now, this thing is only formalized for the reals. So we need to formalize it for the extended reals. So in terms of formalization, we are very much in the early stages. There is previous work that formalizes some propositional differentiable logics. We want to do the same for logic and then extend it into first order. And of course, MATCOM already has a bunch of results, like probability spaces, level X integrals, and we want to leverage all these things. So currently, we're basically extending the library with extra lemmas and stuff. This is like the correct version of the power function, which is nice. And this is ORS, which is a lot of cases. But basically, you have to deal with an exponent that is an extended real number. So it could be infinity. And so you have to do a bunch of case analysis for it. This is like the 5th version of this power function. We are working with people from MatComp, and hopefully this is the one that will get approved to be integrated into the library. And in terms of Hulda, is basically the same lemma that is already in MatComp, except that is for the extended real numbers. That's it. Which means a bunch of case analysis. And that's it.
Questions?
I also have a picture of the entire calculus, just if anyone is curious.
So I'll start off with one. I remember the very first slide, you had all the great things about, you know, the logics that the...
This one?
Yeah, you had, oh, these are the great logical properties, and these are the other ones. So I assume that your system has all of these things, or a subset of these things, or
yeah. So, sorry, I forgot to explain this. Like, I don't have a formal definition in the presentation. The answer is hopefully yes. Okay. But we haven't formalized everything. So like we know it's continuous, we know it's monotonic, we know it's shadow lifting. We are not sure about this one yet.
Okay, okay. But it has...
It does have compositionality, resolution, prelinearity, and we are here. We know it's sound. We are trying to make it complete.
Approximately. Go towards affinity would be the same question. Any other questions? I guess I'll have one more. I was trying to get a sense of what these functions were doing. You had that neural network, right? You had a phi on one side and a phi on the other. So what are these exactly doing?
Right. So this varies from methodology, but imagine this is like a computational graph, like a circuit, where each of the nodes is an operator. So it will be like the semantics of conjunction and the semantics of whatever is connected to that, and so on. So basically you add that at the beginning or at the end of the network and parameterize it over the inputs or something like that.
Any more questions? Well, if not, let's thank our speaker again. And next up is Gregory to talk about verifying hypervisors. Actually, I'm not sure. Not this time. So in fact, he'll be talking about recursive mutexes and separation logic. Thanks.
Thanks, Ben. All right, so so I told you guys this morning about the work we've been doing on program verification for hypervisors. And this isn't about hypervisors, but it's still about C++. And it's still built on this brick program logic. So when we originally built brick, we built it to do the verification of this hypervisor platform. And we talked about the concurrency and all sorts of stuff like that. Lots of interesting questions written in C++, but mostly standalone. And in this talk, I'm thinking about, how do we go from this standalone kind of low-level systems code and move it into kind of more mainstream C++, thinking about more generally embedded systems or device drivers, robotics, server infrastructure, and things like that. And the main thing that I'm going to talk about in this talk is the fact that one of the big differences between this is basically freestanding. We didn't use a lot of the standard library. We kind of coded things to keep them simple, so we could do verification on them. And you go to people who do C++ for real, like maybe the people who work at Bloomberg, and you tell them, sorry, you can't use any libraries. You have to code everything from scratch, and they'll probably just tell you to go away. It's not worth it. What's the point in using a language like C++ if you can't use the millions of lines of code other people have used? So in this talk, I'm going to be thinking about the fact that to kind of expand to the real world of C++, we need to support things like the standard library. And in this talk specifically, I'm going to talk about this very tiny, tiny, tiny sliver of the standard library about mutexes. And mutexes are interesting. This is work with William Mansky and Kay Du at UIC, and they are interested in kind of verification of concurrent algorithms. And we just decided, well, let's start with mutexes. Those should be simple enough. So this is the mutex specification, kind of, this is from cppreference.com, I think. But mutexes are kind of like locks. I'm assuming that people basically know what a mutex is. But the idea here is that a calling thread will own a mutex. So you can't pass threads around, or you can't acquire a mutex in one thread and then release it in another thread. And there are some other rules in here, like mutexes can't be destroyed while they're locked and things like that. So we wrote a specification using Brick for these, and I'll give you kind of the highlights of this. I'm going to note that this is an axiomatized specification, and when we look at specification of the standard library, there are some things that we can verify, but the implementation of mutex is actually very low level, like send signals on these things and stuff like that, and so we're not really focused so much on the actual verification at this level. We have done some proofs in this work, and I'll tell you about them later. So in separation logic, we're going to have a predicate called mutexR. That's ownership of this mutex, and it's going to protect this invariant P. And then you've got a locked predicate. This is pretty standard stuff from separation logic. And using that, we can write specifications like the specification for lock and unlock. And here you can see that we're capturing this characterization that the current thread owns it by adding the thread that did the locking on mutex.locked. And so when you get it back, when you acquire the mutex on a particular thread, you take the current thread and you use it here. And then when you unlock, you're required to be unlocking from the same thread that you're on, okay? So you can technically pass the mutex.locked token to another thread, but they won't be able to call unlock because their thread ID will be different than your thread ID. Sorry. All right. Maybe I've lost people. But you can see basically the strategy here. The beautiful thing about separation logic is even complex concurrent data structures look relatively sequential, right? So we can do the normal sort of, when you acquire the lock, you get access to the resource. When you release the lock, you lose access to the resource, but you're required to reestablish them, okay? So it's the nice part about separation logic. All right, so we can use this to verify a very simple program. And I realized I cut out some of the thing, but this is a simple class C. It's got two longs, an A and a B, and they're guarded by a mutex. And they've exposed methods like update B and update A, which acquire the mutex, increment or decrement the value, and then unlock the mutex, right? So this is a program you can specify it. This is a very simple spec for it. Not really any problem here, okay? Now, if you go and you add a transfer function to this, you might say, okay, what we want to do is we want to make sure we'll take the lock here, then we'll update A, and then we'll update B, and then we'll unlock. And we'll know because the amount of money or whatever that we're putting into A is the same as the amount of money that we're taking out of B, and everything should all work out really well. And you could actually verify this. It would be a nice and simple proof. But the problem is that in the real world, you'll actually get a deadlock here. You already own the mutex, which you acquired on this line, and you're reacquiring it here. Because we care about safety, it's not a problem for our proof, but it's really a problem for the implementation. And the way this is addressed in some systems, including Java, for example, is to use something called recursive mutexes. So the interesting new thing about a recursive mutex is you acquire a mutex. If you acquire it again, then instead of deadlocking, you just say, okay, you have it. You didn't need to do that. So you can lock, and then when you unlock here, you don't give up the resources. You get to keep them. So no one else can come in and grab here until you do this unlock here. So when they say recursive mutex, it's like lexical locking. And this is the concurrency primitive that underlies the implementation of synchronized in Java, which I did many years ago, but I haven't done lately. Okay. I'm sure I've lost some people at this point. I apologize for that already. You can take the implementation of C and change mutex to recursive mutex, and then this code works out fine, okay? So now you're not going to see a deadlock when you try to update A here because this lock will not deadlock you. You'll just increment this counter. And we can then verify this. And now the question is can we write a specification for recursive mutex that looks and feels like mutex in the way that people are used to. Hey, I've got a mutex, let's just change to a recursive mutex so I can handle these new patterns. And what does that actually look like? So here I've got the mutex specification above, and here's the recursive mutex specification below. There are a few lower level details that are changing, but I'm going to say at some level these things are quite similar. One thing that's slightly different about this is an axiomatized characterization directly. We're actually proving this specification holds from a lower level atomic update style specification. So because I presented this in an invariant guarding style, I wanted to show this in the same style. So this is actually a derived specification on top of a slightly lower level specification. Now, for regular mutexes, the two are equivalent. You can prove one from the other in both directions. For recursive mutexes, I think it might be it's at least an opener question to me. I haven't considered if you could actually verify in both directions because of the recursive nature of these things. All right, so we again have the recursive mutex ownership. That's the sequential ownership that we'll share amongst threads. And now, instead of having a single locked predicate, we're basically going to say everyone who's interested in using this recursive mutex needs to have a holds predicate. Okay? And that holds predicate is kind of poorly named, but it says this thread holds that mutex n times. If I don't hold the mutex, I'll hold it 0 times, and that's perfectly fine. But as soon as I start acquiring it, this n will go up, and then it will behave a little bit more like locked. So, I already said that. So basically what we're doing is we're taking the kind of Boolean that we think about here. It's either locked or it's unlocked. We're generalizing that to a natural number where 0 means it's unlocked, and then successors mean it's locked with so many times, I guess, to say. And we can use this sort of borrowing lemma that says if you actually hold the lock, then you can grab this holds thing, and you can actually get P out. That's where I'm actually going to be able to get an access to P. And then I can put it back when I'm done by reestablishing P. And so you can see a little bit here how this might work. If you acquire the mutex originally, you might figure out, maybe you wrote a 3 into that value. So you'll acquire the mutex, then you'll borrow the stuff out, you'll get access to this, you'll maybe update to 3. Then when you unborrow, you reestablish the existential quantifier. And then if you try to borrow again, then you'll lose the fact that you wrote 3 here, okay? And so that's a problem because when you think about that initial program, I called in and I acquired the lock, then I did the update, and I kind of released the lock at the end of that. That would normally require me to unborrow, but then I would lose the information that I had. So we have to fix this. We have to make it so that borrowing and unborrowing is kind of information preserving. And the way we capture this is to extend this n. So we used to have n here, which is the regular natural number. But what we're going to do is we're going to take the p here, which is usually just an mpred, and we're going to expand it by basically the existential quantifiers that are available. So rather than this being just a prop or an mpred, it's going to be a function from number to mpred. And then the numbers that fill in those holes are going to be stored in this args when the value is actually locked. And that allows us to make this borrowing lemma here, which says when you borrow, you get the p at x's, and then you can get it back. And there's another update lemma that allows you to actually change the value of x's here. So now, when you unborrow, you basically get something like this, and then by basically delta reduction, you can get back. So now we can go back and forth. We can go in and out without losing any information. And that allows us to write a specification for something like update. Update A or update B are basically equivalent. It says, I hold the lock here. Sorry, I might hold the lock at the beginning. I don't know. I've got args, but args could be 0, so I don't hold it at all. At the end, it's still a valid lock, and I'll still hold it with the same arg, so the same distance, but I will, sorry, not with the same arguments, but the same number, the same depth of acquisition. but I will have updated the model in this particular way. And this allows me to acquire the lock on the outside and then figure out what updates occurred without having to, this is allowing us to expose those existential quantifiers. And this also allows us to prove a stronger transfer specification, which is the one we wanted. So what did we actually prove here? We proved update A and update B, and we proved transfer up to a little bit of overflow. And we proved these against this resource specification that I showed here. And we proved the resource specification against this logically atomic spec. The interesting thing about these proofs is that none of these proofs require separate case analysis on whether or not the lock was originally acquired or not. Okay, so it really does, the proof still feels very much like a mutex proof, a regular mutex proof, rather than having to reason about, the two cases independently. So that's it for the talk mostly. This is us. And the development we're doing is here. The standard library specifications is an open source project. So you can take a look at the specs we've written so far. We're trying to build this out more in service of people who are interested in doing program verification with C++. So we've got things like CC types and assert and several other libraries. We've got someone working on shared pointer right now, which is kind of interesting. And the brick program logic and the automation documentation, if you're interested in any of that. And that's all I have until my next talk. Questions?
Questions?
Thank you. This may be a bit off topic, but I noticed you have this kerthread resource in your specs, and I was wondering if it is somehow not transmissible from one thread to another, which would not make sense.
It is not transferable to other threads. Yeah.
Okay.
It is a subjective thing, and it's done with
Okay.
monpred.
Thank
Yeah,
you.
yeah.
Thanks. More questions?
Go ahead.
I was wondering whether there was any deep reason why you merged the current acquisition count with the other stuff basically in this access predicate, because it seemed like, then you have to tease it apart again in the spec, and you also were updating one but not the other, which I guess would be you have to tease it apart again for this lemma, which lets you switch between held and holds or whatever it was, and here you have to update just one field. It seems like usually these would be separate, or I don't know.
There is some tying between them, because if n is 0, you don't actually have arguments. You can get them, but they don't mean anything. So the type of args is actually like 0 or successor of something and this other thing.
I see. Interesting.
Yeah.
Okay.
Otherwise, you can't get this property exactly. Well, you can because you know args is inhabited, but it doesn't work out as nicely. You still end up with other stuff.
Okay, that makes sense. Thanks.
Time for one more question, if there are any. Well, if not, let's thank Gregory for a second time.
Thank you, Ben.
Okay, our next speaker will be Mikhail. I'll be talking about mechanizing this JavaScript proposal.
Yeah, thank you for the introduction. My name is Mikhail.
I'm Arya. I'm a first-year master student.
And I'm Björn. I'm also a first-year master student.
So we will be talking today about JavaScript, which is formally known as ECMAScript. The language is specified and standardized by the Technical Committee 39 of ECMA International. And the suggestions that this committee considers are formally called proposals. So essentially, a proposal is a description, is a technical description of a new language feature from various perspectives. And currently, the committee is looking into a few proposals, and we can roughly classify them into three groups. The first one being proposals that introduce new syntax, then proposals that introduce new semantics, and finally the largest groups are the proposals that introduce new APIs for the standard library of the language. So the way that the committee works is that each proposal has a champion group, maybe 2 to 5 persons, who actively work on the design of that proposal. And then when there are committee meetings that happen several times per year, those champions groups can present their proposals and get the feedback from the entire committee. The committee follows a pretty precise process when they consider and advance proposals. So a proposal can be in one of these 6 stages from 0 to 4 with some non-obvious stage numbers. So stage numbers, so each stage has particular requirements on the quality of the specification text, on the quality of the implementations, requirement to have testing, and so on and so forth. But nowhere here we can see any requirement to mechanize anything. And that is kind of expected. This is a huge industrial language, and we cannot really expect that. So we still thought to make this experiment and see whether some mechanization of some parts of some proposals could actually bring some results. And for that we have chosen the largest API proposal, which is called temporal.
Right. So temporal is a proposal to extend JavaScript APIs to deal with like date and time. So it defines a bunch of, or it specifies a bunch of types and functions to deal with date and time, year, month, day, time durations. It also supports time zones and also non-Gregorian calendars. And on top of all of that, it sort of claims compliance with all of the relevant industry standards like RFCs and the ISO standards. And so like this is obviously an enormous topic. It's also a very messy and complex topic. So as mentioned, it is the largest of all the proposals with over 200 pages of specification text. And that is maybe why it's a good candidate for this kind of mechanization, since like no human can hold all of this in their head.
To give some insight into what the specification looks like, we'll show a few examples. So you can see it has a pseudocode style, and here we have a sequence of assignments and arithmetic manipulations. Another example is that we have just a sequence of if statements, and then we have some more complex functions that utilize JavaScript semantics. The proposal has more than 500 functions, and 200 of them have to do with date and time manipulation. We ignore the function that utilize JavaScript's semantics directly when mechanizing. And so far we have mechanized 43 functions and have related proofs to them. And that resulted in 3,000 lines of ROC code. So what do the functions bodies look like? As we've seen already, we have a sequence of conditionals, sequence of let statements, and arithmetic manipulations. But you also have invocation of other functions, string manipulation, nested control flow, and rich text notation. Most of these were pretty straightforward to mechanize in ROC, but some were not.
Okay. So yeah, this is an example of one that caused us a little bit more trouble. This function just converts a timestamp to the year containing that timestamp. And its definition in the specification is just the largest integer satisfying some predicate. And this is like a declarative specification in contrast to the much more imperative and algorithmic functions that are like the imperative and algorithmic definitions of most other functions. And so this doesn't like tell us how to implement it, which we wanted to do. Instead, we just came up with the simplest possible implementation we could sort of convince ourselves was correct, which is just a linear search. But that requires a termination proof, which causes us to need a monotonicity proof, requiring another monotonicity proof, and so on, for about 200 lines of ROQ code for this one function in the proposal. As mentioned, the proposal also claims to be compliant with various standards. An example of this is a function that turns a date time into a string representation, and the proposal says that this string is compatible with RFC 3339, which defines sort of the format for date and time strings for internet interoperability. And so we've mechanized the grammar from the RFC and have a nearly complete proof that the function actually respects this RFC.
So for the functions we mechanized, the most interesting ones have explicit assertions and preconditions. When mechanizing them, we have to prove these assertions and preconditions. But it happened that we failed to prove some of them, and then we verified, and we thought this to be an inconsistency in the specification. And this we verified by proving the negation of the predicates. Examples of these inconsistencies were that a function produces an invalid value, or that the function argument is out of bounds. We contacted the TC39 delegate, Philip Cemento, a champion of the proposal, with our findings, and he confirmed them to be indeed inconsistencies. After that, we collaborated to make changes to the specification text to then correct these inconsistencies.
So, trying to summarize, what are we actually interested in proving when looking into such a proposal? So we could sort of consider three directions. The first one is claims that are about internal consistency of the specification. So obviously all of the assertions and preconditions should hold. And things like this function does not throw an exception is an example of an internal consistency. The second group of claims that we are interested in proving is so-called expected behavior. So this is not explicitly given in the proposal specification text. So we had to elaborate this first. Things like if you add 0 to a time, it will not change the time. Or if you have two equal dates, then the difference between the two equal dates should be 0. Sort of in the style of property-based testing. And the third group of claims that we are interested in proving are claims that establish compliance to external, to various external artifacts, like the one we have heard a couple of minutes ago, that a certain function produces a certain string that is compliant with a certain industry standard. So if you have established all of these different kind of claims, we can be sort of more sure about the correctness of the specification. Sort of coming back to our original motivation to have this experiment and see whether mechanization can somehow help finding inconsistencies in the specification. So we have a couple of reflection points. So the first one is this. So the algorithms in the specification are imperative, and we are trying to use a functional language. So is that a problem?
So like for the most part, it's been pretty all right, but there are a couple of places in our mechanization where the ROC code does not sort of correspond as clearly to the specification text as we'd otherwise like, because we want to, because we're sort of manually translating these algorithms, so we want to sort of minimize the chance of human errors by things like code duplication. But like since these things require some creativity, we might wonder how this could be integrated into the TC39 process.
So we could create a domain-specific language inside ROC for the delegates to use when creating the specification. But do we expect them to actually write ROC code?
Well, this might be a hard sell to the JavaScript community. But what we are currently trying to explore is to use already existing tooling that the community already is using and see whether we could benefit from that. So here I'm in particular talking about ESMeta, which is a tool originally developed by Sukan Ryu from KAIST and her group. So essentially from what we need from this tool for this project is the fact that the tool parses the text of the JavaScript specification and produces an abstracted history. And then we can try to generate some ROC code, at least for some of the functions, like maybe the more trivial ones, and then at least have it as a first step towards having mechanization as part of the TC39 process. But obviously we are far from there yet. The link to our repository is here. Thank you very much. We're ready for questions.
Questions?
You're probably aware that there was a paper on time published at CPP 2 or 3 years ago, which was about the discrepancy between years and physical years. Is it also considered by the standard that you're looking at?
So the specification of the specification of this proposal that the JavaScript committee considers, I don't think they have that, but I'm not entirely sure. At least the functions that we have mechanized were sort of the more trivial ones, so we didn't get to that.
Okay.
Point.
Any other questions? Maybe I'll have another one. So why did you choose to go with the largest proposal?
Well, we wanted to see how much we can actually mechanize, and whether even like mechanizing as sort of a small fragment, so essentially we have like less than 10% mechanized, would help finding bugs and in the specification itself.
How much of the, let's see, you said there was a fragment that you couldn't, sort of mechanize because we relied on JavaScript features. How much lies between sort of things you don't expect to verify and what you have verified? So how much more do you think you could feasibly mechanize?
Don't remember the exact number, but at least like twice as many functions as we have now, I think.
Okay, around 80. Any more questions? Oh, I have one last one. I think on one of the earlier slides you were talking about sort of the second category of properties you might want to recognize. Expected behaviors, and I don't know, in my experience with JavaScript, I wouldn't expect adding 0 to something not into it. So
okay. To fix it.
Okay, with that, let's thank our 3 speakers once again. And a familiar face, 3rd time's a charm. All right, so our penultimate speaker will be Gregory once again, talking about verification of C++ programs.
themes of my talk might suggest this is the only thing I do. It's not, but it's one thing I've done for a while now. So in this talk, I'm going to talk about verification of templated code in C++. We saw a talk by Bloomberg this morning, and there was a slide that had a lot of templates on it. And so clearly, templates are something that are used frequently. And just to make this talk self-contained, I've done a lot of verification of C++ code in this hypervisor stack, which we've seen before. Mainstream C++ uses this crazy standard library, which we saw in the last talk. And one interesting thing about the standard library is not only does it have recursive mutexes, but it also has heavy use of templates. And I would claim that while we often think of C++ was originally thought of as, okay, this is C plus classes, I would say that in many cases, modern uses of C++ is really like C plus templates. Okay, so a lot of the work that's gone on in C++ recently, I feel like has been pushing templates even farther and kind of almost de-emphasizing, maybe to some extent, classes and virtual dispatch. So in this part, I'm going to talk about, so we talked about brick, and you haven't really seen it, but it's a program logic for C++. And in this part, I'm going to talk about how can we take this brick program logic, which is about runtime C++, things that actually run, and kind of glue on template verification. Templates do not run. They're compile time expanded. So let's talk a little bit about how this works. And I'm going to say this, if you are one of these people who doesn't care at all about C++, but you do care about macros, everything in this talk, or almost everything in this talk, will also apply to you. So here's a very simple templated piece of code. This inc twice function is something that no one would ever write in practice, but is small enough to fit on this slide and demonstrate a few interesting concepts. So inc twice is this function. It's templated over a type T. You might think of this as polymorphism. And it increments x, and then it increments the result of incrementing x. And we can call that function twice, inc twice x at type int, and inc twice c at type c. And in this case, it will use the primitive integer increment. And in this case, it will use this overloaded operator ++, which you can do in C++. So right now, we can verify this code. Everything that would actually run in that test main function down there, we can verify. And we just do it like this. We say we're going to verify this function. We write verify spec. And then actually, the proof of this function is just go. It's literally 3 characters that would have been shorter than writing the comment there, because we have reasonable automation. But we still have to duplicate the proof. And this won't scale if we're thinking about doing something more interesting, like vectors or things with loops, where we might actually have to write a specification of a loop invariant, for example. So what we're aiming for is a proof of inc twice, not a specialization of inc twice, just a verification of inc twice, to verify that templated code and then to apply it here. And we want to make sure that this strategy does not enlarge the TCB in any way. So we don't want to have to deal with overload resolution or other problems, and we don't want to add those to our TCB in any way. Okay, so there's a lot of things we had to do. Some of them are described in the paper somewhat tersely due to the page limitations. But in this talk, I'm going to focus exclusively on the question of how do we actually specify templated code. And that looks roughly like this. So here I'm writing a specification for kind of an arbitrary piece of code. One thing to note is we're going to use standard brick syntax for function spec. So it takes an argument that happens to be a reference to the value t. And then we're going to use regular ROC level quantification, a section in this case, to quantify over the representation predicate that represents the ownership of the value of that type. And in this case, I'm just keeping it very simple and deciding that when you call the inc twice function, the representation predicate, the abstract representation predicate that is going to use is going to be a predicate over z's, some numbers. We quantify over explicit substitutions here. So that's going to allow us to not have to think about the whole program, because overload resolution is something that looks at your entire program. And we don't want to have to think about working with this every time things change. So you can think of this as the minimal piece of the substitution that's actually necessary to instantiate this function. And the statement, instead of being a statement about the function, it's going to just be a statement about the body of the function, because every time you instantiate a function, it gets a new name. It gets, in particular, inc twice of int is a different name than inc twice. And the last thing, and the thing where I'll spend most of my time on here, is about instantiation constraints. So we'll need a way to specify what happens when you say plus plus of x if you don't know what plus plus is doing. And this is the way we'll do that. And you know, for most of you, you'll say, well, it's kind of like a function, so let's just specify it as a function and get on with our lives. It's a little bit more complicated than that, and that's what we'll talk about. But if we set things up in this way, then everything's ROC level quantification, so we can just apply this in basically the same way that we saw before and then discharge that obligation. So we'll walk through what exactly that obligation says. Okay, so let's take a look at operator plus plus of x and see how this might work. So what happens, what does C++ do? So when it looks at any particular instantiation like this one or this one, it will figure out the type of x, and elaboration or instantiation goes bottom up. Type checking goes bottom up. So it says, okay, I've got operator plus plus applied to int ampersand. What does this do? Well, in C++, that's implemented by primitive pre-increment. It's a primitive of the language. For the class C, this is an overloaded member function, so we'll call that. But this is just the regular overload resolution. There's nothing template specific inside of here. Things get a little more complicated because when we use this in another context, the lookup now that has to happen is not a lookup on necessarily t ampersand. It's a lookup on whatever type was returned when you called plus plus x. In some cases, this would not be valid code. For example, if you instantiated t with atomic int, it just turns out that the library does not quite do what, in my opinion, is the right thing there, but so it won't quite work. But it turns out that, yeah, so in both of these cases, for int and for C, the return type of plus plus x happens to be the same as the input type. And we can characterize that in our specification by giving a concrete kind of statement. It says the return type of this expression, of an expression of this form, is going to be this value. And the nice thing about being able to do this is that we now know that both of those plus plus operators refer to the same term. Okay, they're both going to be resolved in the same way because the value of x here is t ampersand, and that constraint that I just showed you is saying that the type of this plus plus x is also t ampersand. Okay. And if I couldn't do this, I'd have to give you a specification for not only operator plus plus applied to t ampersand, but also operator plus plus applied to the declaration type of plus plus x, which would be kind of annoying. Okay, so now we're going to focus on this box, which is really about the functional verification portion of this. And to do it, to highlight the kind of subtlety here, we're going to look at a slightly different example. Operator plus, which now takes two arguments. So here, t ampersand and t ampersand are my arguments here. And so we look here at add, operator plus, taking two int ampersands. This operator doesn't actually exist in C++, but there is an implicit coercion called the left to right conversion that will take an int ampersand and return a value of type int. Okay, so that's this EL2R. And then we can plus those two things. So this is what the code that Clang will generate kind of is the intermediate format here. And the interesting thing about this is that when you run this value here, when you run this program, the semantic says you can non-deterministically choose to evaluate this argument first or this argument first. But when you do it, you have to evaluate the whole argument. So you will evaluate like E1, and then this left to right cast, and then E2, and then this left to right cast, and then the whole thing. So what you have to do is you are evaluating, you're intermingling code that comes from the context with code that comes from the holes that get spliced into this context. So to capture that, we use predicate transformers, and now I'm switching back to the pre-increment thing. So apologies for the slight back and forth here. But here you can see what we've got is a lambda that's taking E. This is going to be the weakest precondition, a predicate transformer, for the evaluation of the first argument, the only argument in this case. And then Q is going to be the continuation, what to do afterwards. So this is written in basically a weakest precondition style, and it says you're going to take the value, you're going to have ownership of R at value V, and you'll return ownership of R at value V plus 1, and then continue with Q by returning P. So I said all that. All right. And so then we can nicely, take this, we can verify, we can prove this theorem. I haven't showed you how exactly we do it. It's a little bit interesting, but for people familiar with these sorts of program logics, probably not too surprising. And then we can use it to discharge proofs like this. All right, so that's it. Again, Brick program logic and automation are online, and if you're interested in this sort of stuff, happy to talk more about it.
Questions?
Thanks, Ralph.
Yeah, thanks, Gregory, for the nice talk. Nice to see that someone is finally daring to tackle the BBEG that is C++ templates. So I don't think I fully understood this connection between the non-deterministic evaluation order and then you switch to predicate transformers. I mean, as far as I'm concerned, predicate transformers, very natural way to express your specifications. But what does that have to do with argument evaluation order? And I mean, in this example now there's only one argument, so I guess there's no order anyway.
Yeah, so if you were, the reason that I called this out is because normally you'd think about this as function arguments, right? Like, in fact, the first time we were working on this, we said, okay, you evaluate the first argument, then you evaluate the second argument, or vice versa, and then you evaluate the closure, like the context, right? That's what you'd naively think. But it doesn't work because there's actual interleaving between the code of the argument, f of like the L and the R. These things can be non-trivial expressions, but also the implicit casts can be non-trivial expressions as well. So if you think about this as a function where you say evaluate L and then evaluate R, you won't get a sound proof rule because you won't have accounted for the side effects that could occur in here. Does that make sense?
Okay, and so now how does the spec issue on the next page resolve that?
It's because you're kind of obligated to show how these things get sequenced. If you had multiple arguments, you'd have to say something like E is run, and this post-processing is done on it. And then E2 is run, and this post-processing is done on it. And then I combine the results. So it gives me a way to talk about all of these different pieces, the semantics of each implicit cast, plus the semantics of the whole thing.
So the let star P equals E here is some sort of weakest precondition for E?
Sorry, it's meant to be monadic bind, basically, yeah, of a WP.
Ah, okay.
Yeah, sorry.
Yes, okay, that makes everything a lot more clear, thanks.
Yeah.
I wonder, normally in this sort of templates you have kind of a lot of compile-time computations, right? Does your frontend already compute those and you see the computation results, or do you somehow reason about the results of the computations that happen at the template instantiation time?
I'm sorry, I did not quite understand.
If you have some computation in your template instantiation,
yeah,
does the frontend already handles that and you see all the results, so you don't need to reason about those, or is there some sort of reasoning you do or you plan to do?
You're saying, like, if I have function foo applied to angle brackets 1 plus 1.
Yes, for example.
We see the evaluation of 1 plus 1. No.
We have time for one more question, if there are any. And if not, let's thank Gregory one last time.
Thank you, guys.
So we're already at the end of RocqPL 2026. So we've hopefully saved the best for last year. So our speaker, Kirill, is going to be talking about JavaScript a la carte, I believe, right? Yeah. Oh.
Hello, my name is Kirill. I'm going to talk about extensible formalization of JavaScript. I'm doing my PhD at University of Turku, and my supervisor are Mikhail Barash and Jaakko Järvi. So the first question is why JavaScript? And the answer is that, as we heard before, it has quite well-maintained standard and transparent feature adoption through the T39 committee. It has a lot of dialects that should help to evaluate how extensible modular formalization is, and it's an industrially used language, so it's interesting how the mechanization will be shaped around that one. There are a lot of existing mechanizations of JavaScript, but they are all old and they are abundant, and one of the reasons why it is the case, it's that mechanization in general are not modular, and it's hard to extend them, maintain them, and keep up with evolving language, especially with JavaScript, which evolves fast. So I will tell how we plan to make proof about the language extensible, what we've done so far, and what is yet to be done. And I will start by investigating why it's hard to extend mechanizations. And if we try to extend the behavior around the type of our very small expression language, we find out that it's okay. But if we try to extend a representation of our language, it will fail, because we need to handle all the new cases that appear, and it doesn't scale with the amount of proofs you do. That's an instance of very well-known problem called expression problem. And there is a certain solution to it called data types a la carte. In boxes, there would be a la carte representation of things that are not in the boxes. And the first thing is, how do you encode the type in order to fight the non-accessibility with adding new cases? And the answer is that you split the recursion and the description of the type itself. What is the fixed point that doing the recursion? We will discuss that a bit later. Let's focus now on how the extension looks like. We add multiplication. We add another functor that, and you can see that x in our functor corresponds to the recursive mention of our type that is handled by the magical fixed point on our functor. And here, all we need to do in order to extend our type is add it to a list of functors that are fixed point on by a fix. So let's see how we can write functions on it and then lemmas. So this is the simplest possible function you can write in this small language that just evaluates expressions to natural numbers. And at first, we will need to write a functor-wide definitions for each functor we fix point on. And that's quite simple and corresponds how you will write it on the usual inductive type. But the caveat is that here we don't mention the type that we are going to recurse on, and recursive call is provided explicitly in open recursion style, because we don't know anything about overarching language. Let's shorten it up and see how we then compose them. So it's a fixed point. And so far, the only thing we achieved is to move the payload of our proofs into functor-wise definitions, but things will break as we extend it. So let's return to fixed point operator and see what it actually does and how it described in data types record. It's described as a data type that finds the fixed point of our functor, but unfortunately it allows us immediately to derive falsehood, so it's unapplicable in theorem provers. So let's investigate a bit further what it's actually doing. And by looking at the types it generates, we can see that for each particular type, we can write the definition by hand. And that was noted by Coca-Lacarte paper that is one of the later paper that explores this approach. So then let's do fix as a metaprogram to extract it outside of our language and permit to use it without enabling to deriving falsehood. Composition can also be extracted from language then and made into a metaprogram. But as so far, we still need to manually add our cases. And the trick is, that was also one of the contributions of Coca-Lacarte paper, that with knowing on which type we're doing our induction, we can actually find the functor-wise proofs in our environment. And that will solve our problem and make types extendable by hand, but proofs and theorems extendable automatically. There are more approaches that solve this problem, but all of them suffer from the same downside, is that they are indirect. And if one looks through the papers that try to mechanize existing languages and acknowledge existence of modular approaches, the single most cited reason for not using them is that they introduce indirectness. And Coca-Lacarte approach is the most direct approach out of them, because first one is using the approach built in on interaction trees. Another one, POPL'26, I think, uses containers to encode the language, to encode the class of functors you're allowed to fix point on. And extensible meta theory through family polymorphism extends the compiler itself to incorporate their way of extending types. So goals of this work, which is very much work in progress, is to start with lambda JavaScript, which is existing from mechanization of JavaScript, extend with core control flow, object mutability, and exceptions to see how well behaved the a la carte approach is. And then extend it with reactivity, because that's one of the proposals in T39 pipeline. Probably implement React dialect to compare them, while maintaining the theorem of progress that you can do step if you're not a value. That local closeness is preserved because we don't have types in JavaScript. The reduction uniqueness to disallow rules that just assign error to everything. And then automate it. We use LP to automate our metaprograms because it allows us to store state that we care about between invocation of meta calls. And that allows to implement composition and all the machinery that is required to keep up assumptions about overarching language. And then there are a lot of type classes that make it possible to go between the extension and the language. And those should be generatable itself. So let's see how the extensions are formed. So imagine you want to extend a language with the new feature functor that allows addition of literals. We write our functor assuming existence of some overarching language. We do some bookkeeping to remember the name, because the variable will be abstracted away after we close the section. We remember that our functor depends on it. We assume that there is an evaluation function for overarching language. We implement the evaluation factor for our piece of language we care about. We do bookkeeping again, and that's it. We also can automate it further by writing example section with all the assumptions to streamline the enumeration and bookkeeping about things we know about overarching language. But then we need to compose it. We need to write a fixed point on types. That's manual. We need to map the things we define with things we remembered, assumed about the language in sections. Then we run compose to compose them, and then remember again, because we might need it further in our proofs. So the things that we've done so far, we implemented pieces of lambda.js a la carte, and they include call by value lambda core, conditionals, unrecoverable errors, and mutable references. The thing that suggests that we are on the right track is that if one wants to write interaction between different functors of our language, it does not require to add any code to existing functors. We just write a new functor that knows about existing functors, and then write pieces we care about reduction semantics and syntax. We preserve across all these things a preservation theorem that is very weak, but it's like a sanity check. We automated section templates almost. Then there is a term specialization because section abstract over the variables it mentions, and then we need to re-specialize it back. And instances for tight retracts that work, that define the how we jump between extension and overarching language are also automated. Things that are yet to be done, and there are a lot of them, probably more than listed here, but we interested in taking care of reactivity, of testing the approach on dialects, for example, on React. More language features are required for sure, and the key piece here is that after we are done with the Lambda JavaScript formalization, we can try to implement the feature that is actually compliant with ECMA standard without touching anything that is in another functors. Then, of course, fixed point and composition does not work yet. And the theorems that we want to have for overarching language are also to be proved. And one thing that is very further work is that actual in-language invariants about language constructions are also yet to be even approached. So thank you for listening. This is a presentation. This is a repository that changes very fast. And I want to finish with saying that JavaScript has a well-maintained standard that allows us our mechanization. Extensibility is crucial for keeping mechanizations up for language they mechanize and to make them useful. Functors enable modularity, and metaprogramming enables composition. Thank you.
Any questions for Kirill?
By unique reduction, you mean determinism, basically, or it seems fairly strong. It's a one-step reduction should be a functional relation or something like this?
Like that, if two terms are, I think it's basically this. So if we can arrive to some expression by reducing, there is no two ways to arrive to it. So the reduction is deterministic.
How often does the language change? Like we saw a lot of proposals to change JavaScript are adding libraries and things like that, and most of those I would imagine would not kind of add new features to the language. How often do new fundamental features get added that you need to change control flow or something like that that would really have a substantial effect on the semantics?
Like Signal's proposal about reactivity is one, but the nice thing about this approach is that hopefully we are able to prove things about even non first-class objects of the language, but things that are actually used in practice. And this approach, it suits for doing so. Because, for example, signals that are in reactivity proposals, they are built on top of existing features of the language. But we want to prove how they behave, even if they fundamentally do not introduce anything new to the language.
Thank you.
It's often a difficulty when you want to teach programming to people that they have to learn a language that has all the features right from the start. Do you have the impression that your solution is would provide a good support for teaching material? Because you make it possible to start with a small language and then...
Actually, yes. I never thought about it, but that could work. Yeah, because the simple core, you teach it and then you gradually extend while students watch or even extend themselves. Yeah, that would work.
Okay, any more questions? One last question? If not, let's thank Carol again.
Thank you.
Okay, well, I guess with that, RocqPL 2026 is officially over. I'd like to thank all of the authors once again, all of the audience here for coming and being active and engaged, and special shout out to any of my PC members who are still around. All the organizers, yeah, and my co-organizer, Frederic, yeah, of course. So, one last round of applause.